Ladies and gentlemen, welcome back to Bitcoin Plus Plus Scaling Edition. We're here for the final day on main stage. I'm joined by Abdel from Starkware, who's going to talk about Bitcoin and Starks.
Hi, test. Does it work? Is it okay? Yeah, okay. So hi everyone, thank you for being here. Today I'm going to talk about Bitcoin and Starks, match made in heaven. So for me, those two technologies are really two different revolutions, and I want to talk a bit about how they combine together and why I think that it's inevitable that those two will benefit from each other and can bring a lot of good stuff for Bitcoin, and I want to explain why. So I'm Abdel, working at Starkware. So Starkware is the company that basically invented Stark proofs, and we are using them to build scaling solutions. Right now we have Starknet, which is the main product, which is a layer 2, a ZK rollup. For now, it settles on Ethereum, but we want to expand it to settle also on Bitcoin. I like everything about freedom tech in general, so I'm a big fan of Nostr as well, Cashew, and privacy. So this is the agenda for the talk. So first I will talk about the genesis of this whole revolution, which is Bitcoin. And then some interesting talk that Eli Ben-Sasson, the creator of Starks and CEO of Starkware, a talk that he gave in 2013 in a Bitcoin conference, where he was already seeing a future where ZK could improve Bitcoin. Then I will talk about the shared DNA and the philosophical alignment between Bitcoin and Starks. And then just a bit about Starks fundamentals, without going too much into the details and the moon math, but just to give the high-level intuition about what they are and why they work. And then why also not only there are a lot of synergies between Bitcoin and Starks in terms of philosophical alignment, but also in terms of tech. There are so many natural connections between the two. Then I want to talk a bit about one potential missing piece for Bitcoin that could turn it into a settlement layer. And then I will discuss a bit about what we can build today using Starks, even without any change to Bitcoin base layer. And then I will come back again about the endgame vision for Bitcoin potentially when it comes to using zero-knowledge proofs. And then why I think this is an interesting path to hyper-Bitcoinization in a way that is really aligned with the cypherpunk roots of Bitcoin. So it all began by, of course, Bitcoin, which was, to me, like highly political message, declaration of war on fiat, or if you want to put it in a more peaceful way, you can say it's a peaceful exit to the fiat system. But in any case, it's something that was really a paradigm shift. And Bitcoin proved that you could actually replace institutions by code and mathematics. So this was really a 0 to 1 in so many different dimensions, like economically, philosophically, technologically, in the field of computation. This was the first time where we could imagine to have decentralized systems that are trustless and permissionless. So it was really a 0 to 1. And then I think that zero-knowledge proofs was another 0 to 1 in a way. And so this is the talk I was referring to, which is a talk that Eli Ben-Sasson gave in Bitcoin San Jose conference in 2013. And it's interesting because already back then he was seeing a world where zero-knowledge proofs could help Bitcoin, and specifically he was thinking about improving the way you verify the computation on the nodes and how you can sync on the network and so on. So it's interesting because even before Ethereum existed, because right now the field of zero knowledge and especially zero knowledge rollups is very heavy on Ethereum, but even before Ethereum even existed, Starks were dreaming of Bitcoin. In fact, Starks at this time did not exist in their current form. But already the idea was really exactly the same as what you can do with zero-knowledge proofs today. Instead of verifying by re-execution, you verify using some crypto and mathematical proof. So this was really an interesting vision. And 12 years later, we are still not there yet, and for many reasons. At this time, it was really not practical. It was still at the advanced research stage, but it was really not something practical where you could use it in the real world for meaningful computation and so on. Also, Bitcoin was not fully ready to be able to verify zero-knowledge proofs on the base layer. It's still not today. But we can see that there is some change and more people seeing the connection between ZK and Bitcoin. So maybe it's time again to consider thinking more about this potential future where both will combine together. But yeah, again, for me, both Bitcoin and zero-knowledge proofs are 0 to 1, a paradigm shift. Bitcoin is about consensus by re-execution, and zero-knowledge proofs is another way to do consensus without even re-executing the computation. So I think there are so many similarities between Bitcoin and Starks in particular. First of all, both of them are permissionless technology. Anyone can use them. Both of them are transparent in the sense that anyone can verify what is happening in different ways. And also Starks are transparent also with the different meaning, specifically meaning that they don't require something called the trusted setup, where you have to do an initial ceremony between some participants, and the system is secure only if the ceremony was done properly. Both of them are trustless. They don't require to trust any particular entity. Both of them are using relatively simple cryptography, even more for the case of Starks that are relying purely on hash-based functions. But Bitcoin also is using relatively simple cryptography, hash functions and signature schemes. As I said, Bitcoin is doing consensus by re-execution, while the consensus in the case of Starks comes from the mathematics. And both really have this motto of don't trust, verify. So there is a pattern, so I think it's time to marry them. So in terms of the trust spectrum, yeah, really the notion of trust is really not binary, and this was discussed also in the panel. So it's a spectrum. You have many different flavors, designs, and so on, starting by some multisig, which is more like a trust us philosophy. You need to rely on the honest majority assumption. And then you can have other ways of improving with, for example, optimistic rollups or optimistic designs that rely on economics and incentives. And you rely on the fact that there will be at least one honest actor in the system that will behave correctly. And then you have the extreme part of the spectrum, I think, both Stark proofs and Bitcoin, proof of work and physics in a way. And in the case of Starks, it's trusting the mathematics, and in the case of Bitcoin is trusting physics. So the beauty of Stark proofs is that they are very succinctly verifiable. You can verify them very fast and in a very cheap manner. And in my opinion, only Starks and Bitcoin require zero human trust. Of course, there are some caveats because you can argue that not anyone is able to actually verify those proving systems, even if they are open source, if there are all research papers to back their assumptions and so on. But of course, not anyone is able to review their soundness and everything. So the soundness is a concept in the domain of zero-knowledge proofs. That means the fact that the prover is not able to create a false proof. So this is, of course, a very important property, because if the prover was able to generate a false proof, of course, then it's not trustless. Just to take a high-level overview about zero-knowledge proofs, an analogy you can make is with receipts in a restaurant. if you as a customer, you are the verifier, and the prover is the restaurant that want to prove that you need to pay a certain amount, and how do you do that? Basically, you will do exactly like what a Bitcoin node will do, is that you will literally compute everything. So it's the equivalent of executing the transactions from the point of view of a Bitcoin node. So this is how you come to consensus with the prover that needs to convince you that you need to pay a certain amount. So, and in the case of zero knowledge proofs, it's different, but you have the same aspect. You have the statement, which is in this case how much you have to pay. Then you have the prover, which is the entity that needs to convince you that that you need to pay this amount. And then you have the customer, which is in this case the verifier. So at the end of the day, you have the same result. You are convinced as a customer that the statement is correct. It's just that you have two different ways of doing that. The Bitcoin way will be in this case to recompute, and you sum up all the items and you check that the total is the same. And in the case of zero knowledge proof, you will just verify the proof without doing the additions. So of course, for this particular example, it will be overkill to use a zero knowledge proof because the time to generate the proof will be much higher to just doing the sum, but it's just to give the intuition about how you can come to consensus with the prover. So to be a bit more specific, to discuss about some properties of Starks in particular, because we discussed about ZK, but there are many different flavors and proving systems. So Starks in particular, the idea is that you can prove any computation using just hash functions. And the idea is that the verification is logarithmic with respect to the size of the computation. So to put it more simply, the more computation you want to prove, the better. You will gain more compression, and the ratio between re-executing the initial computation versus just verifying the proof will become more and more interesting. So they have this very interesting property that makes them very suitable for scaling. This is why they are very heavily used when it comes to scaling, especially for big computation. And in particular, Starks, as I said before, they are transparent. So they don't require a trusted setup ceremony, where there is this notion of toxic waste. And you need to, usually in a trusted setup, you need to have at least one party that will destroy this toxic waste. So usually it's pretty good assumption because you can argue if the trusted setup is done properly with hundreds or thousands participants, you can have some confidence that it was executed properly. And also you have the chance, if you can participate to the trusted setup, you know for a fact that it's secure if you are doing it properly. But still, I don't like them because, for example, let's say, imagine in 10 years, you don't know if it was done properly and you did not have the chance to participate in the first place. So I think this is why it's super important to have systems that don't require a trusted setup. And also in the case of Starks, an interesting property that is also very valuable in the case of Bitcoin is that they are post-quantum secure. And why is that? Simply because they rely only on the collision resistant property of hash functions, unlike some other proving systems like Snarks that use elliptic curve cryptography and pairing specifically, and then they are not quantum secure. So the magic, to summarize, is that you can turn any computation into a relatively small proof. It depends on your base, but yeah, usually around 100 kilobytes. The proof size is usually one of the probably only downsides of Stark proofs versus Snark proofs. So some people, usually what they do is that they combine and they wrap a Stark proof into a Snark proof, like for example, gross 16 to reduce the size. But to me, this is not something I really like. I really like the purity of using pure Stark all the way, because first of all, I think it makes the system more complex when you wrap a Stark in a Snark. And it's harder to reason about the soundness of the whole system. And also, I think you can reduce some of the properties of Starks when you do that. But it makes sense. I understand that for pragmatic reason, you want to reduce the size of the proof. So this is usually why people are doing that. For example, in the case of ZK rollups on Ethereum, we are the only ones that are not doing that. All systems, ZK VMs and stuff like that are using Starks, the final proof, they are wrapping it in a snark that they verify on-chain. But we don't do that. We use pure Stark all the way because we don't want to reduce the nice properties of Starks. And one thing that is very cool, they don't add any additional assumptions with respect to Bitcoin because, again, they rely purely on hash functions. So it's not new cryptographic assumptions that you add on top of Bitcoin. So the high-level overview of the process of generating a Stark proof. The first step is called arithmetization. The idea is that, as we saw before, you have a statement that you want to prove, which can be any statement or any program. But in order to generate a proof, you need to turn this into polynomial constraints. So this step is called arithmetization, and this is how you convert a program to something that will be provable. This step is painful if you do it by hand, to call it like that. This is what we did initially, before the invention of Cairo, which is the language that we created to make it more easy. So a fun fact is that, as I said, before the creation of Cairo, the engineers in Starkware were literally doing this for each use case. So we had customers that wanted to prove something, and the idea was to say, okay, how we can turn this program, for example, an AMM, into a Stark proof. So they were doing by hand all the polynomial constraints, etc. So it's very hard. It's time-consuming. It's hard because you need to be really careful about the soundness of the system and stuff like that. And as you probably know, engineers are lazy, so they wanted to find a better way to do that. And they were thinking about maybe creating some kind of CPU that would be provable. Interestingly, Eli Ben Sasson, who created Starks, he was very skeptical. He said, no, it will never work, and so on. And it happened that it worked, and this was the genesis of the creation of Cairo. So the idea of Cairo is really to create a CPU, which will be this set of polynomial constraints and so on, which is called AIR, algebraic intermediate representation. And then you have some some opcodes or instructions, and then you can create higher level programs with that in a much more developer-friendly manner. So we have a high-level language that now is very close to Rust in terms of syntax and everything, and you can just program your program in a high-level language, and you don't have to care about those mathematical constraints and everything. Just writing the program in Cairo, turn it into something that will be provable. So this is something that is very practical if you want to write meaningful, complex programs, like, for example, a virtual machine where you can implement smart contracts and stuff like that. So there is another approach that many people are taking, which is like ZK VMs that are trying to directly prove existing languages like Rust and stuff like that. So most of them, what they are doing is that they are taking an architecture like RISC-V, and what they do is that they are writing those AIR to be able to prove RISC-V instructions. And then it means that you are able to prove a Rust program or anything that compiles to RISC-V. So it's, of course, a very interesting approach in terms of developer adoption, because you don't require the developers to learn the new language if they want to use zero-knowledge proof. Still, we don't want to do that, and we believe that the Cairo approach is the right spot, because even if you can prove Rust with this approach of RISC-V ZKVM, it comes with a huge overhead, because, of course, RISC-V was not designed to be ZK-friendly. So you can generate a proof, but it comes with some overhead in terms of efficiency, both in terms of speed, but more importantly, in my opinion, in terms of cost. Anyway, then the second step is the polynomial commitment. The idea is that the prover needs to commit in advance to what is called the execution trace, which is basically the representation of the execution of the program. You can imagine that you have a program, you have some variables, and then you will have an execution trace where you will have the values for each variable after each step of the computation. And the prover has to commit to that using polynomial commitment. And then you have the FRI protocol, which is basically checking the polynomial correctness and basically low degrade testing. That is an important step in the protocol. And then there is this important step that is to make it non-interactive, because historically, those systems were designed to be interactive. it requires to have some interaction between the prover and the verifier with some exchanges, and then the verifier will do some queries, and then would be convinced that the prover is honest. But of course, you don't want to do that. I mean, maybe you want to, but we think it's bad because it would require that users are constantly online if they want to verify the proofs, and this is something that is probably not not a good thing. But for some people here, I think that they are thinking that interactivity is a feature, not a bug, right? But we don't believe so. So yeah, Fiat-Shamir is something that make the protocol non-interactive. And yeah, as a reminder, it's more or less hash functions all the way down. Okay, so in terms of technical fit, so something that is interesting, especially if, with the new generation of proving systems, is that they are using pretty small fields. So usually when you are doing like some zero-knowledge proofs, it's modular arithmetic over a prime field. And now the modern proving system, they are using relatively small field. For example, for us, with 2, which is our new generation prover, it's using Mersenne 31 prime, which is a 31 bits prime field. And it fits perfectly with Bitcoin script arithmetic because Bitcoin script has 32-bit arithmetic. So it's very interesting property because you don't have to emulate big field operations within Bitcoin script if you wanted to verify zero-knowledge proofs in Bitcoin. Also, the fact that they don't rely on new cryptographic assumptions is a very nice fit. So yeah, I think they combine well together also in terms of the technological fit. Okay, so Opcat. So we realized that it could be actually one simple way to be able to do native zero-knowledge proof verification on Bitcoin. And it's not only theoretical, we proved it. We were able to implement a Stark verifier using Opcat only, and it would be practical. So it's interesting, but we see that it's this change specifically is highly controversial in the Bitcoin ecosystem for different reasons that I will qualify more or less rational. For many people, it's more about the people who are pushing the change rather than the change itself. So I think it's a bit, it's a pity that we are not discussing the change, but more the people who are pushing the change in a way. There are some concerns about MEV potentially, which I think is a valid concern, and I think we want to see more research on that front. And there is another maybe like cultural, philosophical concern about if we bring Opcat, it will turn Bitcoin into something that can do literally everything, more or less. And some people are thinking that maybe we don't want to bring those use cases, like degen use cases and this kind of stuff. It's interesting because now we are at the point where like very small changes into Bitcoin could turn it into something more or less Turing complete. So it will be a turning point, and some people are worried about that, especially in the current context where you see that even just a mempool policy is highly, highly controversial, and now there is huge, I don't know if it's huge, but there is some kind of divide in the community about the nature of Bitcoin itself, whether it's only like pure monetary transactions or more, enabling also some arbitrary data that could make it like a settlement layer. But if you think like that, you cannot really distinguish between like arbitrary data that are useful to build layer 2s or like arbitrary data that are just JPEGs or whatever. So it does not help, and the context doesn't help to be able to discuss properly about this potential change and stuff like that. But yeah, this would be probably the minimal change that could turn Bitcoin into something that will enable settlement for ZK rollups, and then brings all the nice properties that we discussed. Mainly scaling, but there are also other properties, and I will touch a bit about them later. Okay, it's maybe too early to consider changing Bitcoin to do native ZK verification, but we can use them today. Yeah, there are many things actually that we can do today without any change that could benefit Bitcoin. So for example, this is Raito, which is one of our projects. So the idea is simple. You implement basically the same logic of Bitcoin Core when it comes to all the consensus rules, and you implement that in Cairo. And as a reminder, everything that you implement in Cairo, you are able to prove it. So the general intuition is that you re-implement all the consensus rules of Bitcoin in Cairo, and then you are able to generate a proof. And what you can imagine to do with that, you can imagine to do some instant synchronization, so like basically improving the IBD process, because you could just then verify a star proof, and you could prove the header chain, and you could prove, for example, in particular, that a block hash is part of the canonical chain in a way. There are some caveats here, but yeah, this is the idea. And of course, the star proof is way smaller than the data that you need to do if you want to do a full sync. And it's pretty much the same security, and maybe you could argue that it's even better because you trust only math and you don't trust any checkpoints or assume valid stuff that you can have in Bitcoin Core. And it does not require a soft fork. So how does it work? As I said, the idea is that you write a program in Cairo. So this is a high-level overview of the program. The idea is that you will re-implement all the Bitcoin consensus rules, like the proof of work, the timestamps, all the rules, and then you will be able to generate a proof. So specifically, how do we do is that we are taking some batch of blocks, for example, 100 block, and we are also using U3XO proof, because we don't want to prove only the header chain, but we want also to be able to generate SPV proofs and to be able to prove the inclusion of a transaction in the canonical chain. And the idea is that we are using something called recursion, and the idea is that you will use the proof of the previous state, and you will verify it, and then you will output the new state. In the case of Bitcoin, what we call state is simply, of course, the UTXO set representation, and in this case, in particular, we are using U3XO. And then the output will be a recursive proof, and then you can just verify this proof. And we can do that all the way from Genesis to the tip. And then we can continue to update this final recursive proof when we process new blocks. So as I said, the idea is really like to be able to sync very fast and easily. It's not really a sync in the sense that you don't have the data as you would have if you would run a full node, of course, but it can be interesting for some use cases. Also, in the case of IBD, it can be interesting to just add that as a way to bootstrap your IBD, and then you can use that to select your peers, because there are some potential attacks when you do an IBD with some peers that will send you like some fake chains with small difficulty and so on, and it can take some time to realize it and so on. So you could use this proof also as a selection mechanism to have the conviction that a peer is connected to the canonical chain. And then you can imagine to do backward synchronization, but at least you can sync or at least have confidence about the tip of the chain with the proof, and you can do that very fast. And something that is interesting is that, as I said, with the U3XO proof in combination of the header proof, you can verify the inclusion of a transaction in the canonical chain. So this is an example, a real example with transaction on mainnet. So we implemented a CLI that is able to basically take as an input the transaction ID and the proof, and then output if the transaction is part of the canonical chain. So you can imagine to integrate this into like clients or wallets. So we started some discussions with some wallets and other people to think maybe about building ZK-like clients using this. And the idea is that we want it to be like public good infrastructure for Bitcoin. So we are running those proofs, like right now we are continuing to generate those proofs, and we will make them accessible to the Bitcoin community. We can publish the proofs everywhere on some backends, on Noster, and then the idea is that anyone can verify those proofs. So we are right now building an SDK to make it very easy So you can have even a TypeScript SDK that you can integrate, and then with one line of code, you can verify the header chain and the inclusion of a transaction, and you can integrate that in the browser. And we are able to do that because we have a WASM version of our stack verifier. And you can maybe also imagine to integrate that in Block Explorer. For example, you will go on mempool.space, you will have a block, and attached to the block, you will have a proof, and you could verify the proof in the browser. So don't trust verify, but instead of re-executing, you just verify the proof. This is the TLDR of this approach. So what do we actually prove with Raito? So we prove the chain validity, like from genesis to the tip. So we can prove that the block hash is cryptographically linked all the way back to genesis. We prove the difficulty adjustments that we prove that they follow the consensus rules. We prove that every block meets the required difficulty target. And we also prove the Merkle mountain range, which is the data structure used for U3XO. And we prove that it is constructed correctly with the valid root. And then, as I said before, we can use the proven MMR route to construct SPV proofs for block and transaction inclusion. Yeah, so you can just verify the star proof, and then you have the guarantee that the transaction was included into the canonical chain. So let me give you some real numbers. We are able right now to generate the full header chain proof in 6.5 hours, which is actually pretty impressive. Some other people did that. I think the second most performant one is the one from Citrea. They are also doing that, and they are using RISC-0. And I think they are able to do that in something like 18 hours on a smaller machine than us, to be fair. Not that big difference, but the thing is that not only our proving system is faster, but also it's using pure stacks and not wrapping a stack in a snark, which is better for, yeah, no trusted setup and this kind of stuff, and quantum resistance. But also, interestingly, this number is the more interesting in my opinion. We were able to generate a full recursive proof of the whole header chain on mainnet for less than $15. So it's very interesting. Some people have the impression that proving costs are highly expensive and stuff like that. But now with very modern and efficient proving system, we were able to reduce drastically the cost of generating proofs. So the proof size is quite big still, but yeah, it's about 1 megabyte. But this is for the entire header chain. And in terms of memory usage for the prover instance, so it's on one single machine. I forgot to mention, but it's on one single machine. This machine has 248 gigabytes of RAM, and during the process, the peak was around 190 gigabytes. And real-time mode, which means when we catch up to the tip and when we continue to generate blocks and proofs and update the recursive proof, it's less than 100 gigabytes. So yeah, those are real numbers. We were able to generate the proof on mainnet, and we continue to do it, and we will update the proof and make it accessible, yeah, like basically everywhere, and with the SDK. And this is not even the final form of this system, because also another difference with Citrea approach using RISC-0 is that we don't have a SHA-256 built-in or precompile. RISC-0 has one. And as you can probably guess, this is like the biggest bottleneck. And SHA-2 in the field of ZK is more or less the final boss. It's really painful to prove SHA-2 because it's a lot of binary operations, and stack proofs and ZK in general operates over modular arithmetic. So we don't even have a SHA-2 built-in. Also, our new proving system is using, as I said, 31-bit prime field, but the virtual machine is still using the old prime field element, which was 252 bits. So we have to do constantly some emulation of the big field. And this is not with GPU acceleration. And we are working on adding GPU acceleration to the prover. And this is without horizontal scaling, so no proving parallelization. And I think something that could be interesting, especially right now because there are some draft BIPs for U3XO, I think it's time for Bitcoin to consider being ZK friendly for everything. So I highly suggest, and we are discussing with people working on U3XO, I suggest that we start to consider changes that are ZK friendly. So in this case, for example, it would be using hash functions that are way more ZK friendly, like Poseidon, or as a default, Blake 3 is interesting because it's both fast for like normal execution and for proving. But yeah, if we want to go extreme, we can use only ZK-friendly hash function. And in general, I think going forward, it's really time for Bitcoin ecosystem to think about doing changes that are ideally, if possible, ZK-friendly. Of course, if it's not possible, yes, but if it is, I think it's a good idea going forward. Okay, so as I said, we can do many things with Starks today, and I mentioned only one of them, but we are experimenting many stuff, like improving decentralization of mining. We did an exploration with Stratum V2, basically enabling the interaction between the miners and the pool to make it more trustless, because you could prove that the block template and the coin-based transaction is valid, and it will be trustless from the point of view of the pool. We are also doing stuff with Cashew, like using Cairo to define spending conditions for Cashew. It's super interesting because then you can have expressivity and programmability for the spending conditions, but without breaking privacy, because the mint will just verify a proof and will not learn anything about the spending conditions. And it's extremely important in the case of Cashew, because Kali initially wanted to consider doing Bitcoin script like spending conditions, like P2P, pay to public keys, this kind of stuff. But the huge problem in the case of Cashew is that it can reduce the anonymity set. And this is something that you absolutely don't want if you want perfect privacy. So just if you are using a Stark proof, the mint then just verify the proof, and it does not know anything about the spending conditions. The only thing he knows is that you both agree on the conditions. So we did that, we implemented that. We are doing also some stuff for Noster, and we also did a Stark verifier in simplicity, and many things. So those are the kind of stuff we can do today. But I want to also come back about the stuff that we could do with some minimal changes to Bitcoin. And I spent a lot of time those past 2 years thinking about Bitcoin as maybe the ultimate settlement layer in the future. And I was trying to compare it to, for example, Ethereum on many different properties that I consider are important for a settlement layer. And I think actually Bitcoin could be the ultimate settlement layer. First of all, something that is unique to Bitcoin is the thermodynamic security, the fact that with proof of work, you have this external entropy that is securing the network and the connection to the real world. I think it's super nice property for a settlement layer. Ossification by design, it's a double-edged word because it's both a gift and also sometimes it's hard to navigate with it. So the good thing is that it's predictable, it's stable, it's backward compatible. So you know that if you build a rollup on top of it, it won't break in 10 years. But on the other hand, it's true that it moves slower, and right now it's not really adapted to for rollups. So you have to navigate with it and to take time to educate, advocate for some changes potentially. The level of decentralization of Bitcoin that is unique, with a lot of full nodes, and also the fact that it's really accessible to run a full node, and it should stay like this. The uptime, of course, this is a very important property. You want the settlement layer to have maximal liveness property. Also, the credible neutrality. This is absolutely unique to Bitcoin. And yeah, of course, it might have some downsides, like because there is no formal governance, it's harder to come to consensus for changes, but it's also what gives the strength and resilience of Bitcoin. So it's a very interesting property. And the fact that it has this single responsibility principle with a hardcore focus on censorship resistance, and simplicity is good in general to reduce the attack surface. So I think it's also a very nice property for Bitcoin. So yeah, for me, the very important properties are the security, of course, the neutrality, and eternality, the fact that you know that the settlement layer will be there for decades, centuries to come. It's super important. So I think Bitcoin is really close to be what I would call the ultimate settlement layer. I'm happy that many people are trying to push the limits and exploring different designs, like all the BitVM designs and stuff like that, that are an incremental improvement. It's not the endgame vision when it comes to ZK. And also, at the same time, there are also other approaches that are very interesting in terms of scaling, like ARC and all those designs that don't require a soft fork and that have very nice properties. So I'm not saying that Starks and ZK rollups are the only way to think about scaling going forward. In fact, they are not, but they have interesting properties, and I think they should be one of the paths that we explore when it comes to Bitcoin scaling. And yeah, the path to hyper-Bitcoinization will come with many different designs and trade-offs, and at the end of the day, what matters is the optionality for users to choose whatever scaling system they want, depending on their preferences. There is no perfect system, but I think that Stark proofs in particular have very nice properties that could make them a path to hyper-Bitcoinization in a way that is really cypherpunk. Because we talked a lot about scaling, but there is also the privacy aspect that is an amazing property of zero-knowledge proofs that right now, today, we are not using. In our case, we are using them only for the scaling aspect, but we know how to use them in the context of actual ZK, actual zero-knowledge, and privacy. And this is something that, of course, is if there is one thing that is missing on Bitcoin, it's probably privacy. It's as important as scaling, in my opinion. You cannot dream of a world with freedom without privacy, in my opinion. Same for sovereignty. Sovereignty without privacy is no sovereignty. So they have to come together. So we need privacy, we need scale, we need sovereignty, and we need quantum resistance, probably. So, yeah, not everyone agrees about how serious this threat is, but we are building Bitcoin for the decades, centuries to come, so we have to care about it. It does not matter if it is in 5, 10, or 20 years, we have to deal with it. It's one of the things that we cannot hide. This has to be fixed. Same for the security budget. At the end of the day, it has to be fixed. So privacy is missing. Security budget will have to be fixed at some point. Quantum resistance as well. And as we saw, Starks have all those interesting properties that fit so well with this cypherpunk dream of digital cash. So I think, yeah, it's really time to... I'm not saying that we should change Bitcoin now, today, to make it ZK friendly and so on, but at least it's time to take more time to educate, discuss about it, and I think this is exactly what is happening. Just the fact that this scaling edition is heavily focused on ZK is a proof that we are going in the right direction, and this is something I'm very happy about. And yeah, I think stack proofs are an interesting path to hyper-Bitcoinization. Thank you.
We don't quite have any time for any questions right now, but I like that Abdel's final point on the path to sovereignty was quantum resistance. Up next, we have quantum questions by Hunter Beast. Please, another thank you for Abdel and a very warm welcome for Hunter.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Great. So, hi, I'm Hunter Beast. I have been working on the problem, studying the problem of quantum's vulnerability, or Bitcoin's vulnerability to quantum computing for about, I think, closer to 18 months now. So, I think it's one of the more potent and concerning pieces of FUD against Bitcoin. And as a result, I wanted to see what we have as a way to address any kind of shortcomings. I think anything that's valuable enough, people will find solutions for any shortcomings it might have. So first, let's talk about some of the history of what quantum computers, how they've developed and all the things around them. So first, let's see, 1981. That was about 44 years ago now. Richard Feynman, a famous physicist, came up with the idea, the theory. It was just theory, and for most of our lives, it's been theory that we could maybe simulate physics and physical processes with computers. In 1994, Peter Shor came up with a algorithm we call it Shor's algorithm that would essentially was the first theorized algorithm that could demonstrate advantage over classical computers. And in 2000, there was a group of cryptographers that came together that formalized the specification for elliptic curve cryptography. So elliptic curve cryptography is starting to come around this time, get more popular, more feasible. In the 90s, elliptic curve cryptography not only was it sort of military technology, but it was also kind of considered science fiction, sort of beyond the capabilities of ordinary computers at the time. But in 2008, Satoshi would come to use it. He wasn't sure which bit curves he should use, actually. In Bitcoin Core, there were some comments on how on which one to use, and we for some reason he decided to use the strongest security, which was 256-bit. And in hindsight, it was probably a good decision. So in 2003, there was a paper by some academics that came up with the approach for how you might use Shors to attack elliptic curves. They found that you needed about 6 qubits for every bit of the key that you wanted to break. In 2013, Edward Snowden leaked some information about a program he called Penetrating Hard Targets. And it essentially was a program that was tasked with developing a quantum computer that could be cryptographically relevant. And they were working with in a laboratory at the University of Maryland, and they were spending almost $80 million a year on that at that time. It's also possible that somewhere along the line that some of that money went to Honeywell and Raytheon, which are both defense contractors that have programs for developing quantum computers. And so the NSA was heavily involved in quantum computing development from the beginning. And the beginning turns out probably around the year 2000. So the spooks have been at this for a long time. And there's not a lot we know about this, but there are some things we know. One thing is that we do know for certain is that the US government is very concerned about the possibility of cryptography being broken along a certain timeline. And so they released a timeline for transitioning the cryptography suites used by the government to harden their own secrets from being compromised. And post-quantum cryptography was a big part of that, especially at the time. Modular lattice cryptography, also known as crystals to lithium, was the major focus of the CNSA 2.0 proposal. And it also said that set certain dates, 2030, 2033, certain targets in which we need to be transitioned. Additionally, last year, there was some more, how would I say, they seem to be developing more certainty about the fact that along a certain timeline, one thing they wanted was to sunset all use of elliptic curve cryptography and RSA within the government by the year 2035. And also in the year 2030, no new system should be using that. And now, recently, just a few days ago, there was guidance from the SEC and their U.S. Crypto Assets Task Force, where they introduced a roadmap for quantum-safe transition of global financial infrastructure. And they outlined a few important things there, which we'll get into. One thing, before we get started, some fundamentals. There's 3 classes of quantum computers that are being sort of like you can classify a quantum computer in terms of its capability. Right now we have noisy intermediate scale quantum computers. Then you have, if they are good enough, cryptographically relevant quantum computers. And finally, you have quantum computers that are basically no worse than classical computers, and we call those fault-tolerant quantum computers. PsiQuantum is a good example of a company that is working on this hardware. So they have moved beyond sort of the chandelier format. So what we call the chandelier format, it's basically like also known as a dilution refrigerator or a cryostat. And these things have to be very cold, about 2 or 3 Kelvin. And they have been working towards scaling their capability to make these work in a way that's allows you to have more compute, more connectivity, more qubits, more chips, more power, and more cooling. And as you can see, it starts to look more industrial scale. On the right there, that machine looks almost like it's something out of like a Bitcoin miner, you know, like a mining data center, and they're just scaling it up to be more sophisticated and capable. So that's a concern. Physical qubit counts double every 5 years for ions. There's different kinds of quantum computers. Some are based on ions, some are based on superconducting circuits, some for neutral atoms. PsiQuantum's quantum computers are actually based on optical circuits, like Mach-Zehnder interferometers and ring resonators. But there's been a lot of focus on neutral atoms. I think it might be Honeywell that's working on neutral atoms, and so they might have gotten there first. now that we've talked about the hardware, I'd also like to talk about the software. That's the other part of it. A lot of people just think like, oh, the hardware is going one direction. Well, the software that you need for a quantum computer to pose a threat to cryptography is also getting better over time as well, as we realize certain things about the hardware. Before we get into that, let's talk about Shor's algorithm and how that works. So essentially, quantum computers can take, say, a key, some data, and put it, entangle qubits and encode that key in those qubits in a vast mathematical space called Hilbert space. A 256-bit number is larger than the number of atoms in the Earth, but smaller than the number of atoms in the known universe, or something like that. But it's an incredibly large number, and so to search that space, it's considered practically impossible for classical computers to do in any reasonable amount of time. But with quantum computers, they can make use of phase interference and make quantum Fourier transform to isolate patterns in the input. And as a result, they can measure that the output in that computation, and so long as they do it for long enough with other things that we'll go into, but as long as they do it for long enough, they will eventually find the key if they're any good, and at which point they will be able to compromise cryptography. There is some recent developments where originally there were estimates of how many qubits you would need. You would need certain hundreds of millions of Toffoli gates. You would need millions of qubits, especially because of the noise. And you would also, originally they thought you needed 6 n qubits, which would be like 1,500 for the number of bits in the key that you wanted to break. It turns out, so as we start to understand the problem better and the hardware better, we actually didn't need all of those. We can actually, for example, this is just a today example. Actually, I call this a today example because the software was written just maybe last month, where a 6-bit number, which is not large, it's 64, like counts up to the number 64, which is not large. It would only need 18 qubits. But what's interesting is that this was run on a computer that was built 2 years ago, and it's not using all of its capability, even. It's just proving a certain number can be found with this particular software and hardware combination. And there are actually ways where we can optimize this software to use less qubits and also work with noise. So one of the problems with quantum computers is that noise can disrupt their operation. Well, with sufficient post-processing and time and operation, there are ways to isolate statistically important values, and also you can always just test every value the quantum computer comes up with, because classical computers can compute elliptic curves like public keys rather quickly, and so there's no reason not to just test everything it comes up with. And if it gives you a key, it only needs to find that key once, and then you know that you've solved the problem. And There's Pruselka was the paper where they thought there was 6n, and they assumed fault tolerance, like a FTQC, like I mentioned earlier. But Steve Tipakonik, he's a researcher who's been studying this more recently, and he was able to run that on a noisy intermediate scale quantum computer. And there's even better ones coming out too. Like the one he ran on was Torino, which was from 2023. Pittsburgh just came out this year, which has even better error rate. And there's also another cryptographer. His name is Pierre-Luc. He's worked on that and provided feedback. And yeah, well, we just discovered that you only needed 3n gates. So there's a possibility that this will match the timeline. We might even be surprised. But there's also another question of like the economic viability, because people are spending billions on these machines, and it costs millions to run them. And there's different sets of coins out there that in different kinds of addresses that would essentially be vulnerable and could be taken to various degrees of legal hazard. But it's also not all state actors have the same laws, so we'll see. According to Project 11, there's 6.6 million coins out there that are held in addresses where we know the public key, like it's present on chain, and that's roughly represents a third of the Bitcoin money supply as of this month. Now this is just taken from the paper I mentioned earlier that was recently published on the 3rd of this month by the SEC, the Security and Exchange Commission in the US. And they have this task force, and they're talking about the possibility for an emergency migration need, and that we would need to upgrade to PQC. What's interesting is that traditional payment rails can't always just hire experts and upgrade their systems, and they'll have really probably no trouble if this happens. They can rewrite their ledgers and freeze Swift and just reverse funds. They can do all sorts of shenanigans that are not possible in Bitcoin. And so, what do we do? What do Bitcoiners do? I'm not here to like just scare you and put out a bunch of FUD and give you no solution. I'm just saying like we need to be prepared and paying attention to this problem and take it seriously. A number of people have told me that quantum computers aren't real. Well, that's an interesting statement, but it's not a strategy. We need, I think, it would be prudent to have a soft fork waiting in the wings, just in case there are this gets any worse. And so, I've been working on BIP360 for a little while now, and it's gone through a number of changes. Who here's read a version of BIP360? Raise your hand. Yeah. Okay. Well, it's going through some changes. It was originally called pay to quantum resistant hash. Now we're going to call it pay to TapScript hash. It originally also specified that it would be a SegWit-v3 output type. Now we're just going to go with SegWit-v2. The reasoning behind SegWit-v3 was just that we thought it might be easier to remember, and we call this like a mnemonic. That's because if we went with the version 3, it would give us in the address. So native SegWit starts with BC1Q. Taproot addresses start with, which are SegWit v1, start with BC1P. And we thought, well, you know, if it started with BC1R, people could remember it for being quantum resistant, so BC1R. And so it might make that association, make it easier to visually identify a bit360 address. Unfortunately, this was not met with much enthusiasm by many of the core devs, and so we relented and were like, okay, well, we'll go with SegWit v2, which codes for BC1Z. And so I guess we'll just have to remember Z means it's quantum resistant. And what's nice about Taproot is that, so this is based on Taproot. Bit360 is sort of like a fix for Taproot. It takes out the elliptic curve cryptography portion of address generation, which is how Taproot works. So Taproot essentially generates an internal key and then tweaks it by what's called a Merkleized alternative script tree or MAST of scripts that are possible for that wallet to spend from those for the coins in that address. And so when you go to spend, you get to pick, your wallet will pick which script path to use. And it's been proposed that we might just disable key path spends in the event that there are quantum computers. I'm not sure I fully agree with that. And that's why we decided to make an entirely new output type, a new address format, that it's technically not an address format, it's an output type, is the technical term for what we've created. And it so it's opt-in. It's fully opt-in, and there's a transition, a migration period, that sort of thing. And your wallet, if we solve a number of other problems, which I'll go into, will be able to allow the user to decide between post-quantum cryptography or elliptic curve cryptography at spend time. So really, there's like no risk in using BIP360 once it's activated. And also, I'm working on a sidechain platform called Ondero, and so we have a quantum working group with a few other people on it, and we've made some changes to core, provided some test vectors, Python Rust examples. We're working on a Signet. We actually have a Signet now, and a mempool.space instance, I should say, and also wallet integrations. And we're hoping that we can have something viable and ready by the end of the year. Now, let's go into the post-quantum cryptography. So, this SLHDSA, or stateless hash, digital signature algorithm, also known as FIPS 205, which is the government designation. It's for the Federal Information Processing Standards that the government uses, the US government uses to protect its secrets. They have a standard called, it uses an algorithm called Sphinx. It was developed by Daniel J. Bernstein and some others. DJB, or Daniel J. Bernstein, is a pretty well-known cryptographer that also has, in the past, created other elliptic curve implementations. There's the Edwards curve ED25519. It's used by Monero and also Signal. And it's pretty trusted in the cryptography community. Sphinx uses a number of other things that have been in existence for a long time. Winter notes, when some signatures actually have been around since the 80s. And it combines them in what's called a hybrid tree, so like using these other cryptographic primitives. The reason we chose SHA-256 is because there is hardware acceleration for that, and crucially, there's no new security assumptions. So, so long as SHA-2 remains unbroken, which I personally believe it'll stand the test of time for a long time, I think. Just based on my research, but there's always a possibility that we're wrong. But and like there was earlier on less confidence in this, and so we actually studied MLDSA and SkiSign and Falcon and a number of other signature algorithms. But we arrived on Sphinx and SHA-2 because these are superior to one-time signatures in that if you reuse a one-time signature algorithm, like especially coins protected by them, you run the risk of exposing your private key over time. And that's unacceptable. And so we, especially in modern Bitcoin, we have the capability for RBF, and there's just also legitimate reasons to reuse keys, one of them being proof of reserves for exchanges in cold wallets. And so that's been we've done a ton of work on experimenting with this algorithm and optimizing it. And there are some other things to consider, which are signature aggregation, which could lead to further optimizations and throughput for Bitcoin transactions. Right now, we have it at TPS, or transactions per second, of like maybe about 5 to 8, depending. This could bring it down to just like 1. And so one way to address that concern is to maybe potentially introduce Stark-based signature aggregation at the block level, coordinated by miners. And also, one other concern that we've identified is that BIP32X pubs are not really going to be viable with this scheme, so that will require some advancements in wallet design for multi-sig wallets and watch-only wallets to communicate public keys and secure them and make sure that they remain useful and available when needed. So this is just like this whole slide is just we're looking into the various different hardware platforms in which hardware acceleration exists for SHA-2. It's evolved over time. iOS has had SHA-2 acceleration for a long time, and it's also starting. It was pretty widely available in server components like AMD EPYC processors around like 2017, and then it started making it slowly into consumer hardware. This laptop here is a ThinkPad P14S. I think it's like Gen 6 or something like that. It's the latest one they sell, Lenovo, and it does support in the Ryzen APU SHA-2 extensions, and so we've been testing on this computer. And we see here's some benchmarks. So we see an improvement of about 2.5x for these signatures. One moment. For key generation, signatures, and verification, and sort of thing. And we've also investigated, so the specific security parameter set that we chose is known as SLHDSA SHA-2 128S, which is a NIST-1 configuration, and it results in a signature size of almost 8 kilobytes. And the public key is only 32 bytes. And it uses this thing called DMSPR. It's kind of the equivalent to, if you've heard of ECDLP, elliptic curve discrete log problem. DMSPR is what secures Sphinx. There was a vulnerability found in Sphinx by Bernstein, the creator, in 2023, which was, Sphinx was originally introduced in 2015, but it went through a number of revisions when it was introduced to the security community for evaluation by the National Institute of Standards and Technology. And before we go into that, I do want to kind of note that NIST is kind of like a blessing and a curse. Like, they're great because they do a ton of work, and it's public, and it's for the public good, really. They do all sorts of things like running time servers for us to all know that we have the same time, and they run an atomic clock, and they standardize weights and measures, and have all sorts of cool standards. But they also work hand in hand with the NSA. And the NSA is known to not necessarily be too terribly trustworthy, especially in the past. They were found out to have actually distributed a broken version of a random number generator for a signature algorithm called 3DES. And this is outlined in a Wikipedia article on what's called kleptography, which is cryptography designed to steal secrets, not secure them. And so there is definitely like some skepticism from, which is fair to acknowledge around NIST. But I think you also have to think of the incentives around this. And I think it would make sense for the government to not introduce cryptography to secure the government secrets. So if we just use the cryptography the adversary uses, then to secure Bitcoin, I think we might be okay. And yeah, and Bernstein discovered that the more secure versions, like the higher security levels, NIST 5, which is like a 256-bit equivalent, is potentially broken, but fortunately the 128-bit version is not affected. And that said, SLH DSA still needs a BIP. We're working on that now. And so Alalula Suntukun, also known as Roast Beef from Lightning Labs, he has turned his attention to this and done a deep dive into the hypertree that's used for Sphinx key generation. And also, Conduition is another cryptographer who engages with the Bitcoin core mailing list, or well, Bitcoin devs mailing list, I should say. And Ethan Hallman is a co-author of BIP360 and also is contributing to the effort to standardize SLH DSA for the purpose of Bitcoin address and key generation. We do need in that BIP to define derivation paths for wallets, have a portability format for multi-sig and watch only, as I mentioned earlier. We need to know which op success codes to provide the opcode for opchecksig verify. And then it just needs to be standardized. We need to pick one. And also, we don't need to bump the version of TapScript, because TapScript has its own versioning system needed for this soft fork. There's also some other work in this space I want to mention. So QBTC uses MLDSA, and it's interesting. It's basically like it's supposed to be like maybe some kind of fallback for Bitcoin in case it's completely compromised. And it uses post-quantum cryptography by default. And they have their own fork of Blue Wallet and their own implementations of various Bitcoin RPC methods for wallet compatibility. And we actually are running it on the, or will be running it on the Andro sidechain platform. And so there's a bridge that we developed for the specific purpose of being quantum resistant, a quantum resistant bridge. One thing I probably should note is that all currently existing versions of, say, BitVM are based on Taproot, which the problem with Taproot is that Taproot addresses, all Taproot addresses are based on elliptic curve cryptography. And so regardless of how you might prepare them or use them, if you only use the script paths, there's still this internal key that's been generated that a quantum computer could potentially get into and spend those coins using a key path spend, and that's not good. And so we actually had, well, when I first came into the project, they're actually using a Frost multisig based on Taproot, and I told them that's not a good idea. And so we had to redesign it, and then we essentially established a protocol for how we would handle these coins in this bridge in a way that would be quantum resistant. And so for that, we use a pay-to-witness script hash, like a native SegWit multisig, ordinary kind of like what you might use with a cold card or a seed signer or a foundation passport. And also, we so Andro is incubated by Mara, and Mara runs another service called Slipstream, where we're able to actually submit the transactions to the Slipstream service and bypass the public mempool, so we don't actually reveal the public key when we go to spend the coins for either like aggregating peg-in inputs or peg-outs, so issuing peg-out transactions. And these signatures would then be submitted to the private mempool that we operate, and as a result, they would not be exposed and vulnerable to quantum computers. Additionally, there is always the possibility that the chain reorgs, and then when we submit these transactions, a block is orphaned out there, and it has these public keys exposed, but it's not actually, the coins aren't actually really moved. And so the way we handle that situation is just by having more keys for an adversary to have to handle in order to take the funds, which makes it a harder target. So, and we're also we have that implementation of BIP360 in core, and we're going to put it into a sidechain that we currently have operating in testnet on Andro, which is called Coordinate, and we hope to have that also available around the end of the year. So that's really kind of like the state of where we're at right now in terms of the, I gave you an overview of the hardware, the software, and then the mitigations, the solutions, and actual real-world implementations and our means of addressing this problem. So definitely go to bit360.org and just read what we have there, and there's some resources there for you. And hopefully, like I don't want to scare people. I want us to be prepared, not scared. And so, yeah, that's why we're doing all this work. Thank you. We have 5 minutes for questions. Any questions so far?
Yes. Hunter, can you tell us what were the objections of the core devs? Why were they not so enthusiastic?
Oh, well, I mean, I think core devs has generally been very supportive, but the thing is, they just nitpick on the specification, the details, and we've done our best to address those concerns. In fact, we've rewritten the BIP a number of times, and their objections I mentioned earlier were just like, just certain like specific things like the version of the SegWit address output type, and also the name of the output type. Originally it was like quantum resistant hash, now it's TypeScript hash. I think there was also like a because we separated out the post-quantum cryptography to a separate BIP, there was a perception that BIP 360 didn't really need to mention quantum as much, like the quantum threat. And so that's why we kind of softened that language and altered it and adjusted it to address those concerns. Does that make sense? Cool. I think there's a question, there's a few more questions actually. I can't hear you.
No. Yeah.
Okay.
How does the practical adoption looks like in terms of the node operators, the miners? Does it require any kind of hardware change that would be a bit controversial? How do you see that happening in practice in the next few years?
Yeah, I think the hardware out there for like running SHA-2 on a node, like there's a lot of like node in a box companies out there like Start9 and Umbrel that will. I think that's going to be a solved problem pretty soon, and so I'm not too worried about the hardware acceleration needed for like signature verification or key generation. It's actually going to be more important for wallet hardware to be more up to date, and so signers might need to update their SOCs and whatever they use, and so. And then, like as far as like a deployment of a soft fork, it's that's going to be a challenge, and we're definitely trying to make it so that the actual technical details are as uncontroversial as possible, so that there just aren't technical objections to it, and we're also doing our best to make wise specification decisions and explain them and be transparent and explain our reasoning, and so hopefully it'll be just abundantly obvious that we need to make this change or not, and ultimately the market decides, and so we'll see. I'm not. Personally, I'm not too worried about this because either it's needed and then everybody just comes to the conclusion, yes, like this is obviously needed, or it never happens. And so either way, I think Bitcoin's fine.
That makes sense. And for miners, because you mentioned wallets and you mentioned nodes, but for miners, would that require any kind of significant investment, like reaching?
No, actually, no. Just they would just need to upgrade their node software. And
that's it.
Yeah.
Okay.
Yeah.
Thank you so much.
Mm-hmm. And I think there was another question over here. I'm curious.
Yeah, thanks. Super interesting. So you talked about the reasoning for hash-based signatures instead of lattice-based post-quantum signatures, and I understand the point about not wanting to introduce new assumptions. Mm-hmm. My question is, like, in your research, do you, on a personal level, like, did you find anything that makes you concerned about the security of lattice-based signatures going forward, or do you think that would sort of, I mean, they have the benefit of producing smaller signatures?
Yeah, no, well, the signatures can be pretty similar, actually. You can tweak the security parameters of SLHTSA to produce signatures almost in the 4 kilobyte range, which is pretty interesting, especially if you're not as concerned about address or key reuse. There's also, let's see, another aspect of that question. MLDSA, right. And so MLDSA, actually I really like, because there's a number of implementations of that are very mature. So like the reference implementation of most of these things is probably not adequate for production use. But Amazon, for example, has created a MLDSA implementation that is based in C, and it has considerations for constant time key generation and handling of the secrets within the software. And so it's actually MLDSA is actually kind of a bit more mature. And also, notably, signature verification and key generation are much faster. The problem with this, though, is that it's just introducing like lattice cryptography to Bitcoin Core versus just cryptography that's based on SHA-2, which is already integrated in Bitcoin Core and heavily used. I think it's just like a less friction there. I do like MLDSA a lot. One algorithm I don't really like is Falcon, and there's a couple of reasons why. One is one of the bigger problems with it is that it's based on floating point mathematics, and which if you on various targets and different hardware targets, the floating point math can vary, like just different details. And even in my own testing of it, I've come into edge cases, and so it actually needed some revision. And it was being reviewed by NIST. It was actually like a close candidate. They even came up with the name FNDSA for it. But the problem is it just hasn't been able to necessarily satisfy all those things yet, though I think they're working on it still. And also, it's just because it's still somewhat new and immature in some ways. Falcon's not new, but because of these concerns and things that are being done to address the concerns, FNDSA is, or Falcon, I mean, is for it to become standardized, needs more time and work, and so it's just not as mature and ready. MLDSA, I think, could have actually been a really good candidate for, like, say, Lightning channels, and there's still more room for BIPs, and because these are taproot addresses, taproot style addresses, right? They have like kind of like tap scriptable outputs, we call them. They allows you to use tap script in the output, tap leaves, right? And so you can commit to MLDSA keys in your address generation in your wallet whenever you generate an address, along with SLHDSA and SecP 256K1. And so you can have the whole mix, and once these are activated and available on mainnet, then you can also spend them. But your funds aren't stuck because you can still use the SecP path, script path spend. So hopefully that makes sense, like it's all pretty well considered. Or
Yep.
Yeah, okay.
Thank you.
Thank you.
Hi. So when to activate this? Do you have like a threshold you're looking for, or what is the activation process? When would you press the red button on this?
Well, ultimately that's not my decision.
I know, but
yeah. I mean, there are a number of warning signs we could see. I think one of the things we might eventually see is, so in the US, any company that's working on advanced technology, like that's considered to be of strategic importance to national security, they have essentially political officers. And so there will probably be some kind of like executive order or directive that comes from the US government that says, do not use your advanced technology to attack Bitcoin. and because they also have other interests, right, in Bitcoin, as we're starting to see. And so that might be like one indicator that, like, okay, well, if the government's saying they'll go that's illegal, then well, that's cool, but that's not cryptography, right? That's not how that. So like, we kind of lost the plot there, and so as a result, we need to have the cryptography to back it up, right, to secure Bitcoin. Otherwise, it just goes to being a system of, you know, like ETF mempool-less trades or transfers, custodial nonsense, and just completely captured and secured only really by proof of prison, right, not proof of work. And so essentially, like, for us to navigate through that, I think just keeping an eye on what the authorities are worried about is probably what we'll need to do. Unfortunately, quantum computing is not sovereign computing. It's not something that we can just like take into our own home and run the actual source algorithm necessarily on our own hardware and then see, like, provably that the security is broken. However, there are ways to prove that it is broken unequivocally. Taj Dreja actually came up with a script where all you have to do is just insert SHA-2 in between the public key from the witness and the check verify. And if you can spend a coin that has a script where the public key is hashed, then you know that a quantum computer probably had a hand in play in that, because like a hashed public key is not really a key. And so yeah, so there is a script where we could just look on chain and say, like, if you could spend this, then it's pretty clear that there has been some break in the elliptic curve discrete log problem, ECDLP.
That's about all the time we have. We're actually 5 minutes into the break. Thank you so much, Hunter. If anyone has more questions, feel free to ask Hunter afterwards. We are on break until 2:15. That's about 6 more minutes.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition.
Ariel from Fairgate, thank you very much. Please give a very warm welcome.
Okay. Is there something with the screen? Okay, just 1 second. Excellent. Okay, thank you. It's a pleasure to be here. I'm going to be talking today about Flex, a solution that we developed to a problem that we have been fighting during the last year when we have been working on the design of trust minimizing breaches. And it makes a lot of sense to start thinking about capital efficiency when you are trying to design a bridge, and there are a lot of trade-offs and a lot of things to consider. So I will tell you a little bit about what we learned and how we package that that experience into this protocol proposition. This is Sean work. I work. Everybody calls me Futo. Ariel Futaransky. I did this together with Sergio at Fairgate. The structure for the call today is I'm going to start with an introduction, describing a little bit about the problem and how we are thinking about it. Then I'm going to describe this protocol called Flex that we designed. That is, we think it's going to be helpful to a lot of projects in the near future. I'm going to zoom in a little bit into the details, and we will see if there is some time to talk about some of the variants of the protocol. Okay, let's start with the beginning. Most of the of course, the bridges that we are thinking about developing or that we are designing and working on, and a lot of new protocols related to the BitVM family, a lot of applications that make use of some of the advancements of that the BitVM family bring to the Bitcoin world. They rely on using, of course, bonds to secure part of these operations. On the paper, we focus mostly on the bridging application because it makes a lot of sense. It's the first thing that a lot of people are building on Bitcoin right now, but it makes sense to take a look at some adjacent applications, and more or less the same rules applies. What I'm going to be talking today is the setting where we have a predefined set of watchtowers that are monitoring the applications, these optimistic applications running on Bitcoin. And we are going to be using some of the recent advances in the ideas related to garbled circuits and how garbled circuits and MPC in general can be used to improve these optimistic applications on Bitcoin. So security bonds or security deposits are used for three different things. It's used to make it economically unfeasible or a bad game in the long term for adversaries to try to cheat and get an advantage. It's also used to reimburse the honest party of any protocol fees that he needs to incur because of the interactions with the cheater. The idea, the motto, in a sense, is a cheater always pays in the end for the protocol fees. That's something that should happen. And in a sense, this is also related to the fact that we need to discourage griefing attacks where some adversaries can pool resources to try to bleed the honest parties and get them out of capital so they won't be able to participate in the game. So the economics of security deposits has to deal with all these aspects. And in the end, the easiest solution, or there is some tension to try to add security deposits and add more money in order to protect and make things work. But there is a strong or a very significant cost associated with these security deposits. We usually don't, when designing some of the protocols, we're not, most of the time we're just assuming that we will be able to use them, but there are a lot of nuances to using these security deposits that have to be taken into consideration, that these 3 points I think are really, really important. The way to think about the cost of having the deposits on the contract protecting some breaching money is directly related to opportunity cost. This money could be on a different financial application giving shield. So the way to think about the actual cost of having the money there is the opportunity cost of what can I be doing with this money on a different application. And the immediate corollary of that description is that the actual cost is not linear with the time that the money is placed on the deposit, but grows exponentially, as we would expect from any system that gives yield where you can reinvest. And the other important factor when we are thinking about designing all these applications is that as the DeFi ecosystem associated with Bitcoin grows, the shield associated with Bitcoin will only grow, so the problem is going to be bigger. In a sense, the opportunity cost is going to be bigger and bigger. So this is a really important problem that has to be tackled and considered. And from most protocols we are designing today, we are choosing to use static bonds. Mostly, static in this sense means that the operators or the parties, the watchtowers, they put a security bond on Bitcoin, and the security bond is there for the whole duration of the protocol. Sometimes that means anticipating putting the bonds there for years to come. We are assuming, we're doing some tricks in order to reuse bonds between different UTXOs or between different parts of the protocol, and that makes sense. But in the end, we are kind of driven by the fact that using static bonds is much simpler. So when we design the protocols, we kind of tie things with the static bonds, and it's much simpler because we're using emulated covenants where we have different parties pre-sign transactions, and pre-signing these transactions in principle requires knowing the transactions IDs. So knowing the transaction IDs means that we need to know the source UTXOs that we are using to fund these transactions. In principle, there are some solutions to this, but most solutions are kind of built on the idea of I know where this funding is coming from, and so the funding is not going to be able to move to any other part during the lifetime of the protocol. So that is really expensive. So the problem with this design, of course, the benefit is simplicity. The problem is that the bonds are going to stay there for the life cycle of the protocol, which might be years. Most of these protocols create relationships between each pair of operators and watchtowers, which means that in a sense, or for most protocols, the capital requirements for bonds grows quadratic on the number of operators because you have quadratic number of relationships. And sometimes you can do some trade-offs to try to reduce these needs, but mostly will end up affecting security. So this is a really hard problem. Besides the actual costs, having the cost themselves, having high cost means that the range of possible applications is reduced because you can only run applications that can support high fees. And if you need high capital in order to participate as a watchtower, then decentralization is also affected because you have only parties which can support that kind of investment participating in the end. So I'm going to talk about our solution to this problem, which is called Flex. Flex is, in principle, a family of protocols. It's like a basic recipe to handle the security bonds. And in this case, what we are able to do is to have dynamic security bonds, which means that these bonds are funded from UTXOs that are unknown at the time of setup for a protocol, and that are only used during the potential dispute period. That's the goal here. So in principle, I'm going to be talking about the two-party protocol. As I mentioned, for most of these applications, we're thinking about it two-party, but we are having the big pictures always means all of the possible relationships has this scheme supported. So the main insight with Flex is the idea of, yes, let's use garbled circuits, that is the hype at this time associated with the BitVM world, it makes a lot of sense to use garbled circuits, but let's go a little bit further and use 2 garbled circuits instead of 1. That is the trick. In a sense, from an MPC point of view, when you're saying, let's say, doing multi-party computation, there is always the idea of using 2 inputs from 2 parties and having this joint computation between the 2 parties. So in a sense, this is really MPC as it is in the beginning, but it makes sense to think about this as 2 symmetric circuits that does the same calculation. That is the idea. We have GCA, which is built by Alice. GCB, that is built by Bob. It's the same circuit, but each of them provides their own secrets and garbling information to the other party. And the idea is that at some point in the protocol, Alice is going to provide some inputs to her circuit. Alice, in this case, is the prover and is probably going a peg out. And as inputs to her circuit, she's providing a proof that the peg out should be accepted because it's correct, maybe with information from some other sidechain. But from a point of view of what we are building here, this circuit is validating the claim from Alice. And what Bob is going to do, Bob is going to take Alice's input and kind of provide the same equivalent inputs to his circuit, the circuit from the verifier. And the idea here is that, as with the BitVM 3 proposal, both circuits are going to be generating a conditional reveal, depending on the result of the predicate. If the predicate is wrong, Alice's circuit is going to reveal something for Bob. And if the predicate is correct, Bob's circuit is going to reveal a secret that Alice is going to use. So the basic idea is that we have this primitive that is the deposit transaction, which is going to be handling the deposits. The deposit transaction is connected with the transaction graph. That's the yellow connector. There is 2 copies of this deposit circuit, one that is used by Alice and one that is used by Bob. And the idea is that this transaction, this is signed with the hash anyone can pay. So the actual funding money comes from the blue UTXO on the bottom. And this means that this transaction now has an unknown transaction ID, but that is fine. We're going to solve it anyway. So as I said, we have 2 copies of these transactions, one for the Alice deposit, one for Bob deposit. And these transactions has unknown transaction IDs. But the fact is that depositing in the protocol, both for Alice and Bob, requires for them to reveal the circuit inputs. So after both or any of them has provided their funding transaction, there are 3 conditions or 3 spending paths for the deposit that are associated to each deposit. Alice can basically claim the deposit if PA, the secret associated to the acceptance of the circuit predicate, will let Alice claim the deposit. Bob can claim the deposit if PB, the secret associated with the rejection of the circuit, is revealed. And if there is a timeout, that means that the other party have not provided circuit inputs that is not available. Then whoever is the depositor, either Alice or Bob, for each copy of this circuit, is able to reclaim the deposit. That is the basic idea. And this is the primitive that builds Flex, basically. These are 2 independent transactions that can be used to manage the deposits, each one with 3 spending paths. 2 of the spending paths then are using secrets revealed from the garbled circuits, and one is a timeout. So how will this work as a complete protocol? Well, we have this the setup phase where Alice above exchange Lamport public keys for a circuit of some other mechanism to allow to provide inputs. They exchange circuit materials. That is the garbled circuit information that will let them evaluate in an encrypted fashion the circuits themselves. They cosign the transaction DAG, so they know they are available. And at some point, there is a peg-in transaction that gets connected to this transaction graph. And then at some point, let's say that Alice will initiate a peg out. On the Flex paper, this is described as a reimbursement protocol because this is very described mostly in the language of a bridge where Alice is going to be advancing funds to some bridge user, and Alice is going to be reimbursed for that initial advance of funds. So Alice starts the peg out by including a transaction that activates the connectors that are interacting with the rest of the protocol. Then Alice posts her security deposit plus the input labels, the LAN port signatures for her part of the circuit. And then Bob posts the security deposits plus the corresponding circuit input labels. He needs to also replay Alice's input labels, so both inputs correspond. Bob needs to post the same inputs or the labels corresponding to the same input that Alice posted before. And this can have different potential interactions depending on liveness. Let's talk about the happy path. What we call happy path here is a protocol interaction, but both Alice and Bob are present and they cooperate and work with the protocol. And the idea is that both operators they provide the security deposits and they provide the inputs to their circuits. So it's necessary one of both PA or PB must be revealed because each circuit only has a single output bit and one of the two conditions must be met. So if PA was released, then Alice wins, collects her deposit. She also collects Bob's deposit at that point and completes the peg out. She uses PA to also complete the peg out and take the funds. If PB is revealed, then Bob collects his deposit and Alice's deposit. He's being reimbursed for the protocol expenditures associated with this interaction. And he can use PB to block the peg out process. And we also have some considerations in the case that either Bob or Alice fails to participate. We assume that one of the parties is honest and is participating and the other is not participating. And we can use timeouts to handle those cases. If Bob fails to participate, he is not providing his security deposit. At that point, we have some time spent by Alice waiting for a timeout to occur. And at that point, she can recover her deposit. And then there is a timeout condition, also a time lock condition on the lock UTXO that she can use to extract and recover. And if Alice fails to participate, she starts the peg out but never provides her security deposit or never provides her inputs. Then Bob can claim his deposit again, or claim Alice's deposit if she did the deposit but did not provide the input. So this is the basic workflow for different liveness scenarios for Flex. This is the complete transaction graph as is present on the paper. Here what we are seeing is the Alice deposit transaction and Bob deposit transaction. These are the two symmetric parts that we mentioned. There's three spending conditions for the deposits as we described, plus when the actual funds that were protected by the bridge can be spent. This looks a little bit more intimidating, and I think it makes sense to spend some time looking at the details of the transaction graph, but this basically mimics what we've been talking up to this point. I will talk a little bit about some Flex variants and why I say that Flex is a family of protocols. Let's first say that, so I mentioned a lot the symmetric characteristic of Flex, but in principle, there's always a first mover. in the protocol that I described, Alice was the first mover. So there is always the chance that one party is going to be, in principle, overspending or spending more money. There is asymmetry that needs to be handled. There are some ways to try to tackle that problem, and I'm going to talk about that. There's also the fact that I kind of simplified the protocol description because I was trying to do something that is more easy to digest. And I kind of brought together the security deposit and the provision of the circuit inputs. That means that for the protocol that we describe, Alice is always providing the security inputs, and if Bob fails to provide her part, she's spending some unnecessary money. We describe this as a non-refundable circuit input publication problem on the Flex paper. There are more details there, but assuming there is possibility of validating the pegout without requiring the complete input of the proof from Alice, that sometimes is can be done if you have visibility of a sidechain or layer 2, where you can see that, yeah, Alice did some operations that makes her the honest party here when she's trying to collect or complete a pegout. So if you can verify the pegout, then you can kind of postpone the publishing of the inputs until someone say that wants to do a challenge, right? So depending on the circumstances, it will make sense to do this that I'm describing, and the cost of the inputs, it might be important. For example, if Alice is publishing the input for a Groth 16 with Lamport signature scheme, it's going to be a significant amount of virtual bytes. We just discussed some ways to, in the previous talk, so there are some ways to reduce that cost also, but it makes sense to have this into consideration. When considering how to solve this problem, there are three possibilities. The first one is, okay, let's use a static security deposit that we can use to repay Alice if Bob doesn't participate when he said that he was going to participate. That for us is a no-no because we are trying to avoid static security deposits as much as possible. That is what we are trying to gain here. The other possibility is having Bob do a pre-deposit. That means Bob is going to be giving a deposit first, then Alice can add her deposit and provide the inputs. This pre-deposit is going to be paying for the reimbursement of the costs of the transaction fees for the input. And then the Bob will be able to fund the rest of his security deposit if he wants to continue with the challenge protocol. And the other possibility that is also described on the paper is completely separating the deposits and the inputs. That's something that we do there. That's a little bit more complicated. But let me show you how this pre-deposit is handled on Flex protocol. The idea here is that this happens with these pre-signed transactions just before Alice is able to run the dispute TX transaction. That was the equivalent transaction on the previous diagram associated with the start of the pegout. So the idea is that in this case, Alice is going to mine the start transaction. This start transaction will have a possibility to let Bob here do a pre-deposit. Again, this pre-deposit can be funded from a previously unknown UTXO. So this pre-deposit is going to have an unknown transaction ID. And there is a timeout and a time lock protocol here that lets Alice continue with her protocol and do a pegout if Bob doesn't show at that point. But if Bob shows at that point and creates this Bob pre-deposit transaction, then this protocol continues, and we are basically in this scheme here. This is connected to the previous protocol that we described. I know we didn't enter into the details of the complete transaction graph, but it's the same idea. We can have a pre-deposit transaction and then connect with the original graph. So there is more information in the paper about the other variants and several other protocols that are constructed in the Flex family. But let me tell you why we think or why we are excited about this. Well, I think the solution to the dynamic on-demand security bond is really, really important for the ecosystem in the short term and also in the long term when yield on Bitcoin goes up. Applications, this applies, as I said, applies mostly to bridging because we are mostly thinking about bridging or lending applications as been discussed, but there will appear a lot of additional applications in the DeFi world in Bitcoin shortly. And this let us fix most of the problems associated with using static security deposits, reducing the total cost and the length of time that we need to have the deposits block into the protocol. This, as I said before, this is really good for the kind of applications that we can support if we have lower values associated with these bonds, and it also allows decentralization. Okay, that was the talk. Thank you very much.
We have time for a question before our next talk. Nope, perfectly concise. Thank you very much, Ariel.
Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025.
Hello everyone, I am Ekramal. I'm one of the co-creators of Citrea, and today I'm going to talk about building Bitcoin bridges with garbled circuits. I know you heard this term before. I will mostly talk about how to build bridges and also a little bit about how to prove the correctness of garbled circuits. So before that, let's start with the previous state of the art. That was like BitVM 2. And let's talk about some terminologies. In BitVM 2, there are several types of transactions. First one is the assert transaction. This is a transaction where the prover or operator puts the ZK proof on chain. And we have a time lock. This is like optimistically verified ZK proof. If in 7 days there's no disproval, we assume this disproof is correct. It was a valid proof. But if there's a disproof transaction, then we burn a connector UTXO, and on chain, we prove that the ZK proof was incorrect. So since the assert transaction is big and the disprove transaction is big, it's like 1.3 megabytes for the assert and 4 megabytes for the disprove, we often hide this under a challenge transaction. So this challenge transaction is a small transaction, And if there's no challenge, we assume that there's no need for a proof. If there is a challenge, then the operator needs to put the proof on chain. And what we do is, like in this challenge transaction, the challenger pays operator for the assert transaction fees. So this is how it looks like. These whole small rectangles are assert transactions combined, and this is a really large disprove transaction, sadly. So what we want to have is, like, we want to reduce the number of disprove transactions that are needed. So we designed a round-based mechanism which allows parallel withdrawals, and with a single disproval, you can stop a multiple malicious activity. And I think this is a really good optimization for this kind of large transaction, and this is also what enables garbled circuits to disprove a single chain of round transactions. So a round transaction has a single round connector and multiple kickoff connectors, and it goes the same with a time delays in between. So it starts with round 1, and in 1 week you can go to round 2, and this goes on. And we have this kickoff transaction. A kickoff transaction means an operator wants to withdraw money from the bridge. And this might be a malicious or an honest kickoff. A malicious kickoff would be an operator trying to steal money from the bridge without paying anyone anything. But an honest kickoff would mean if an operator paid 10 BTC to a withdrawal to the user, then this would be an honest kickoff. So what we do is the reimbursement transaction would have an input of the next round transaction. So that means without going to the next round, operator cannot take any funds from the bridge. And yeah, this reimbursement transaction also has the input of the 10 BTC deposit, and the top arrow is pre-signed at the time of deposit for all the operators. So if we burn this round connector, the operator won't be able to send the next round transaction, meaning that the operator won't be able to get any reimbursement. So the property we want is, if the operator is malicious, we just want to burn the round connector, and that's it. If there are multiple kickoffs, operators trying to steal like hundreds of Bitcoin, we can just burn a single connector, and then no funds are at risk. So this is the beauty of the round transactions. But there's some problems. What we want to have is we want to enable a lot of deposits and withdrawals. WrapBTC currently has a total of 400,000 BTC burn and mint, which means if our bridge denominator is 10 BTC, our bridge should support 40,000 withdrawals. But every round output is for a single withdrawal. So, which means we need a lot of outputs and a lot of round transactions as well. So in Bitcoin, there is this thing called dust limit, where a UTXO should have at least 330 sats for this transaction to be standard. And if you do the math, the initial collateral requirement goes up really fast. So what we designed is we designed the round transactions non-standard, where except the round connector, every output is 0 sats. It doesn't have any value. It's just a connector output for these pre-signed transactions. And with this, we can have infinite amounts of round transactions. It's just a matter of pre-signing. And with Bitcoin Core 29, we can also spend 0 set outputs in a standard way, because with Bitcoin Core 29, pay to anchor and truth transactions, if ephemeral anchors are added, where we can have inputs with 0 sats, a single output to add the child transactions for child pays for parent, and this is a standard transactions now. Okay, so how do we combine these DK verifiers with round transactions? Remember, we had this challenge, assert, disprove transactions, and we have this round transactions. It's just simple as connecting that round connector with the disproved transaction. And that's it. So if the operator puts an incorrect proof, we can send the disproved transaction, burn the round connector, and stop the operator indefinitely. OK. So with BitVM2, as I said, it was like big transactions. With garbled circuits, these transactions become really small. The disproved transaction is around 200 bytes, and the assert transactions is around like 2.6 kilobytes. It can actually be made smaller than that. So yeah, this is how it looks like. This is currently, I would say, is probably the smallest optimistically verifiable ZK proof on Bitcoin. It's just a bunch of Schnorr signatures that are adapter signatures. And this is how it looks like. This single small square is a single small ZK proof, is a gross 16 proof. And this is the comparison of the transaction sizes between BitVM2 and garbled circuits. This one, assert transaction, this was for old Lampert signature type. This is actually smaller than that now with the adapter signatures. And this is another size comparison. Now, this per transaction is much smaller. And also, assert transaction is really small as well. OK. Another good optimization by Fairgate Labs is transfer of ownership protocol. I'll briefly talk, but this reduces the operator front covering problem. This eliminates it, where in exchange for exponentially pre-assigned transactions with the numbers of operators. So what we do is, like, for each deposit, every operator generates new keys, and we sign the reimbursement transaction for every subset of operators. So if you had like 10 operators, we would sign the reimbursed transaction for 1,024 different addresses. And when the user is doing a withdrawal, every operator encrypts their private key and sends it to the user. And then the user selects which subset it wants to go with. It will probably select all the operators that have sent their private keys to have the maximum security. And then user finalizes it and writes it to the rollup, and the rollup writes it to Bitcoin. And at the time of withdrawal, the money goes to this subset, and user can take it from there. The idea is, if at least one operator is honest, that honest operator won't try to steal money, and then only the user will get the money from that output. So how it looks like with this, instead of the kickoff now commits to the subset of operators, and the reimbursement goes to this subset of operators, and the user can take it from there. So TLDR, there's no collateral needed for stake because now the disproved transactions are really small. There's no 4 megabyte transactions. There are still some non-standard transactions within the round transactions, but those are non-time critical. There's no front covering, and operators don't need to hold any liquidity. It's just user gets their withdrawals after a time period. And it's still trust minimized. But there are some drawbacks, and I want to talk about them. One is, as I said, this transfer of ownership protocol requires exponential signing. If you had like 30 operators, it would be infeasible. But what we can do is we can combine this TOOP with our previous approach, where if the user wants, an operator can front cover with the old approach, and then operator can get the reimbursement. So we can also combine this TOOP with the old design. OK, the other problem is how to prove something about Bitcoin. So we have these ZK proofs. How do we know where is the Bitcoin? How do we know if a withdrawal happened? How do we know the state of the rollup? And this is like a well-known problem. We call it Bitcoin Light Client on Bitcoin. So the solution is, it's kind of simple. At the challenge transaction, the challenger also puts a proof of longest chain proof. this longest chain proof can be compact as 144 bytes. It's a single gross 16 proof, and the total work. That's it. And then the operator has to come up with a longer chain. So there are ways, some ways to do this. One is using op returns. Now with Bitcoin Core 30, we can have large op returns. But this adds a step where a watchtower first initially sends this transaction, and then it also needs to send the op return transaction again. The reason of this is the op return changes the TX ID, so we cannot pre-sign this transaction. So if we could have taproot annex, we could simplify this transaction graph by 2 times. And this would reduce the waiting time as well. While in this transaction, Watchtower can commit and sign the longest chain proof, and then the challenge is automatically sent in a single transaction. With the op return, we need 2 transactions. OK, now let's talk a little bit about garbled circuits. So a garbled circuit is actually a binary circuit of a ZK verifier. This is an example gross 16 verifier. It actually has a lot of gates. It has 10 billion gates, where 2.7 of them are non-free, meaning that they have a storage cost. So before going into that, we need to prove that a garbled circuit has been garbled correctly. And I want to briefly talk about the cut-and-choose approach for this. It's really simple and intuitive. The way it works is the garbler generates multiple garbled circuits and commits to them. This action can be done on Bitcoin. The garbler just commits to them and writes it on Bitcoin. And then the watchtower, or the challenger, randomly selects some of them. In this example, we select 2 of them. And the property we want is at least one of these are garbled correctly. If an operator can predict which 2 of them will be chosen, operator will make this garbling incorrect and can fool the system. But yeah, after the challenger selected the 2, the garbler, the operator, needs to reveal the unselected ones. It reveals all the data about them. And everybody can check if they were right, if the revealed ones are garbled correctly. And after we select the 2, we can combine these 2 into a single garbled circuit. We can just glue the input wires together, solder them, basically. So, as I said, the probability of operator cheating is basically predicting which subset will be chosen. And we can change these variables. In the literature, the state of the art is like, not the state of the art, in the literature, 2 to the minus 40 is chosen. And if we had like, if you want to reveal only 3, if you want to choose only 3, then the operator has to garble 18,000 different garbled circuits. So we wanted to find the sweet spot. Yesterday in the BitVM Alliance, we did some cost analysis. And this is the clearer table. It's basically, if you choose the parameter, if you choose 5 garbled circuits out of 700, then the storage cost would be 200 gigabytes. The garbling cost would be $7, and 10-year storage cost would be $670. And this is like one-time cost, while, not the storage, but the garbling. While setting up the bridge, every operator does this, and for years, this can work. You just need to store this data. And yeah, from our research, this seems really promising, and we're going to go with this. And you can read our research here. thank you for listening. And if you have any questions, please ask it.
The floor is now open for questions. Please raise your hands and I'll come over with them.
Does the design reuse the Garbled circuit?
So it doesn't use the Garbled circuit if an operator is honest, because a Garbled circuit is used when there's a challenge. So you can think of it like there's permission set of challengers and permission set of operators. We assume at least one of them are honest, and if the honest challenger doesn't challenge if an operator is honest, then that Garbled circuit remains there indefinitely. So it kind of, the design makes it such that we don't need to reuse a Garbled circuit. We don't use it if we don't need it.
Can we use this for quantum liquidity, like liquidity that backs something and yet is not?
Like quantum liquidity?
Yeah, like the Heisenberg's liquidity, like liquidity at the same time as backing, and it's not a concept you're familiar with?
I'm not familiar with. I only know that with these Garbled circuits and using a lattice-based snark, we could build a quantum-resistant bridge. It needs some changes, maybe BIP 360 or using Lampert signatures. But yeah, with Garbled circuits, we can do quantum-resistant bridges.
Do you have any ideas about how to support permissionless challenging, as in BitVM 2, for the snark validity?
Yeah, I have some ideas. The idea there is, okay. So we have this Garbled circuit different than, like in a different place than the round transaction, and with this we cannot do this. We need to have these before generating round transactions. We need to bake this into the round transactions. So what we do is like we create a transaction in between rounds where anybody can challenge. And yeah, with the cost of generating Garbled circuits per round transaction. But I haven't done the full transaction graph yet. I'm just doing research on that now, these days.
Until you're not. So if you're building like self-healing liquidity, like which anticipates liquidity challenging event and self-heal, so that like you're always liquid, like is it something that's possible with this?
I'm not sure I get the question. Okay, we can talk after the... Okay.
Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025.
The panel and introducing the rest of his panelists. Matthew Vuk from Second. Please give a warm welcome to Matthew. Thank you.
Let the panelists come up to the front. So we have Philip from Tanarati. Come on down. Yep, right at the end, right at the end. We have Adam from Atomic Labs. Come on down. And we have Alex from Arc Labs. Come on down to the front. Right in the middle, yeah. Yep. And we have Yoavella from Fama Labs joining us momentarily. Come on. So, yeah, make sure our microphones are on. So we're here today because each of our panelists is working to build Bitcoin so it can be usable for everyone, by everyone, not just technical power users. So we'll begin with some quick introductions. So please introduce who you are, what you're building, and what is the one thing you're most proud of shipping at the moment.
I'm Alex B. I work at Arc Labs. We're shipping an implementation of the ARC protocol called Arcade, and we're getting close to mainnet. That's why I'm excited.
I'm Adam from Atomic. Currently, most interesting thing is we are getting our EVM implementation ready for mainnet, basically, now deployed on Citrea testnet and looking forward to deploy on other Bitcoin L2 rollups.
Hello, my name is Philip. I'm building Tanarati. Tanarati is the cell phone financial platform on Bitcoin built on Citrea network. And we are preparing the testnet version and so to be on mainnet after the Citrea launch.
Thank you. Philip, you have a very novel product that I'm really interested to learn more about, and you aim to kill seed phrases and have a biometric first Bitcoin wallet. So you're using facial recognition and fingerprints. Would you be able to tell us a bit more about your technology?
Yeah, sure. So we're using technology called passkeys, and thanks to Citrea's technology, we can actually leverage that in order to be used for Bitcoin and Citrea. And what it means is that people can actually create their account or let's say wallet without ever having seed phrase. which we think is really powerful because there, as we know, a lot of problems with keeping the CFA, storing it. How do I save it? Maybe for us who are in the space for years, it's not a problem. But if you give it to someone who's completely unfamiliar with how Bitcoin works, then it gets tricky, right? So in the case of passkeys, what you can actually do is that you have your Face ID or fingerprint enable you to access the passkey that's stored on the device, which means that you basically have a hardware level security, and this part of the hardware is completely separated from the rest of the hardware on your phone, which means that no one else, neither Tanarati application or Google or Apple, can access it. And then when you see it, how users actually react to it, we think it's really powerful because it lowers the barrier of how do I get access to this Bitcoin on Citrea.
And you really believe this is safer than having a 12-word passphrase?
Yeah, I mean, it's not that I believe the technology exists for a few years out there, and it's not just used in crypto and blockchain. It's been fully tested out there yet. So we, just leveraging what already exists, and now we can finally apply it to this part of the Bitcoin.
Great. I would love to hear from the other panelists if they agree that this biometric way of securing your Bitcoin is safe and something they would use with their own platforms.
I think passkeys are very widely used in the overall Web3 ecosystem. And it seems to be proven that this is how regular people can easily start interacting with the crypto world. And just bringing this back to Bitcoin, I think, is very valuable.
Yeah, I agree completely. We have plans to hopefully be able to offer similar using our own platform. So, I mean, it's a trade-off. It's a one that I think is increasingly, the reality is that if you look at any other ecosystem other than Bitcoin, it's kind of become the standard. And so, it's going to be each to their own as far as how much money you're willing to save using these techniques. But clearly, as far as I'm concerned myself, I have a, non-negligible amount of money secured by these passkeys. I would put my life savings on it, but I think it makes everything very convenient. And if this is a panel about user experience, it certainly creates the best possible user experience for anyone that's, has devices. It doesn't require any additional device. I think that's kind of the key to this. As much as I think the hardcore Bitcoiner crowd is a fan of additional hardware for cold storage, clearly this hasn't taken off in the mainstream, and it's probably unlikely to do so until the form factor improves considerably, or maybe until the secure element chips on some of these popular devices like the iPhone actually are able to secure, are able to support, Bitcoin's cryptography curves.
Thank you, Alex. And I would like to welcome Yoavella to the stage. Yoavella, can you give us a quick introduction about yourself and what you're building?
Sorry, I was lost. Yeah. Hello, everyone. I'm Yoavella, co-founder of Fama. So we are building trust minimized Bitcoin bridge infrastructure and also application using this infrastructure. It's for the trust minimized Bitcoin bridge. It's utilizing BitVM, and then we are also founding member of BitVM Alliance. So I'm very interested to what everyone's building and want to share more about what we're building.
Thank you very much. And Philip, one more question for you. You described a system of guardians, and that's in the case that you lose your device or you can no longer biometrically unlock your own device. Can you explain to us how the system of guardians work and what prevents guardians from colluding against the user? As we know, Bitcoin is adversarial.
Yeah, sure. So the biggest question that we get is what happens if I lose my phone and my device and I have passkey on it, right? And the answer is that, well, you have several methods that you can use. One of them is called social recovery. And how it works is that you say, I have a few people that I trust, so your family, your friends, the people that you know well. And then you say, I will add them from my account as guardians. And what it means is that if you accidentally lose your device, you can actually send them a request to recover the account for you on a new device. This is kind of also powered by the technology that we have on the Citrea network, but it's not the only one. Passkeys can be synced across devices, which is also fine if you trust, for example, Google or Apple to do this for you. So it's basically you can choose your own level of safety and the trade-offs, right? When it comes to guarding specifically, you can add 5, 10, 3, whatever you want, and you can put a certain amount of threshold. So you say like, I have 3 people that are my guardians, and I need 2 signatures in order for this to be recovered. And what this means for users is that like, not only they don't have to worry about seed phrases and this complicated tech of hardware wallets, right? But they can have additional methods on top of that in order to be additionally secure for their funds. Why are guardians also interesting to me is that we can also use them for different stuff. For example, what I think is really important for users and user experience in using Bitcoin and spending it is like limits. For example, that means you put your own rules and say like, whenever I do a transaction that's more than 0.1 Bitcoin, I want additional approvals so that I can actually send it. And guardians can play a big role in that with, of course, the presumption that you believe them and those are the people that you trust.
Thank you very much. I'd like to move on to Adam from Atomic Labs. It's my understanding that Atomic Labs is a reference to atomic swaps. Is that correct? Can you please explain to us quickly what is an atomic swap?
It is. So atomic swap is a protocol whereby 2 parties can exchange assets, be it on 2 different blockchains, in such a way that either both parties get the assets they want or none of the parties get the assets they want. Usually how this was done before is through the use of this hash time lock contract, and this was known, and this is how Lightning works for the past 10 years, even more. But we were taking a different approach there. So the swaps, as we're building them, are still atomic, but the atomicity doesn't come from the hash time lock, but it comes from the Bitcoin Lite client that we have on the other side. So how it works, we basically wrote a Bitcoin Lite client. So this is basically a software that verifies the header chain of Bitcoin and proof of work as an EVM smart contract or a Starknet smart contract or a Solana smart contract. And with this primitive, the side chain or the other chain can basically fully verify if something happened on Bitcoin or not. So we use this primitive to be able to do these atomic swaps without HTLCs, because I mean HTLCs, they come with their drawbacks of like free option problem. They're trustless, which is nice, but the free option is kind of a big limitation when it comes to swaps between different assets.
Thank you. I understand also that HTLCs have some type of liveness requirement in addition to the free option problem. Can you elaborate some of the ways that the liveness requirements can hinder user experience?
Yeah, correct. So a lot of the solutions, I mean, including Bolt, which is the most known in the Bitcoin space, actually aren't trustless if you're going from Lightning into Bitcoin. Because for them to really be trustless, you would have to wait for the first commitment transaction to be confirmed before you go and claim, so reveal a secret. And this is simply like a very bad UX, because you would need to have the user be live and have the web page open for 10 minutes on average, but it could be hours, right? This is the only way how you can achieve the trustlessness with these HTLC atomic swaps. Whereas with our solution, this is kind of not required, because you're not dependent on someone revealing or not revealing a secret. You use this Bitcoin Lite client to trustlessly prove that something happened or didn't happen.
Thank you for elaborating. Now, Alex, I would like to first of all congratulate you on your private mainnet launch of ARC recently at Baltic Honey Badger in Riga, Latvia.
Thank you.
So congratulations on that. We did our first Bitcoin transactions with Lightning, and we actually used Bolts, which Adam is mentioning right now, as the Lightning gateway for it. Can you tell us a little bit about how that works?
Sure, absolutely. I mean, Bolts was an early partner for us and kind of like the obvious solution to enable kind of interoperability with ARC and sort of like the wider Bitcoin ecosystem. And we worked quite a bit since pretty much October last year in terms of implementing, the HTLC swaps that Adam was referring to. And the neat thing about it is that we were able to create a pretty impressive user experience from the fact that we wrapped this up with a BTC Pay server kind of plug-in implementation. So the experience for the conference goers in Riga was such that they were all able to use regular Lightning wallets. Probably must have been at least 10 different versions of Lightning Wallet from custodial to self-custodial used by attendees during the event. And the attendees were paying the merchants sort of point of sale system via just a normal Lightning invoice. But on the back end, Bolts effectively was processing these payments and doing a reverse swap back to Arcade, which is our implementation of Arc, meaning that the merchants were actually receiving virtual UTXOs in a way that has sort of very strong trust minimized properties, but without, while completely abstracting away the notions of channels or liquidity, which has kind of like been the biggest pain point in Lightning, especially for receiving payments throughout the years. So we managed to achieve a very slick UX. And again, this was all a trial, but we're pretty excited about where these things are going.
Thank you. Well, Adam shared some concerns about HTLCs and bolts. Do you think that these are relevant to ARC?
I mean, there's certain aspects that translate certainly to ARC, and I think at the end of the day, yes, again, these are all trade-offs, but you know, effectively, when you're also receiving payments on ARC, regardless of when it's coming from a Lightning payment or a regular ARC transaction, you also don't have this sort of like Bitcoin finality concept that I talked about the other day, wherein obviously, as long as you receive a transaction that hasn't made it into a Bitcoin block, you cannot expect to have Bitcoin security on that transaction, or at least Bitcoin finality. So what you have is a copy of a transaction that you can actually broadcast on-chain to be able to claim the funds. But there is a scenario, and this is what people have been referring to kind of like a state chain trust model, wherein you know, the previous owner of the VTX that was forwarded to you might be able to collude with the operator of the system to kind of reorg or double spend the transaction that you receive. Now, there's a lot of contingencies that are put in place to avoid that. The number one being really just the incentive of the system and the operator expecting a profit from his operation. And obviously, these are things that are, I mean, at the moment that the double spend would happen, it would be quite easily detectable by the users of this system, and a large portion of them are expected to have direct spending pad on chain, so they would exit. And so overall, yeah, I mean, the HTLC model for us continues to be the correct option, but you know, I'm also interested in what Adam is doing, and we're contemplating the possibility of doing cross-chain swaps as well, and I do believe that what he's implemented is probably the correct model for that.
Thank you very much for sharing. I'd like to bring it over to Yoavella now. So I've heard that your product is now live on 11 chains. Can you tell us about why you're launching on 11 different blockchains and how you see it that it's integral for Bitcoin to be bridged to these different places and not kept on a single Bitcoin layer 2?
Yeah, sure. So we just launched our first BitVM bridge implementation on 11 chains from Ethereum-based Arbitrum to Aptos and Say, so including both EVM and non-EVM chains. And then even though we've already integrated with these many chains, which means that user can mint Fama BTC using BitVM bridge super easily. But however, in the beginning, we are focusing building liquidity on selective chains. So far, we have around, I guess, like last time I checked, it's over 2 million of TVL on Aptos and Say, and then the volume, our bridge volume in the past 3 weeks is like over $3 million. And so far, most of it is retail activity, so we haven't talked to any big LPs, even though some of the liquid funds are very interested in using the BitVM bridge to utilize their Bitcoin treasury. So far, it's all like retail activity, and then we still have a cap, like 3 BTC for a pre-deposit. And then, so the reason being, like, I know that a lot of bridge, when they first launched, they're focused on, I'm launching, one chain and the other, because there's like liquidity constraint. So we realized that. But on the other hand, for us, we are like, really, engineering focused team. So we, my co-founder have over 7-year experience in ZK, and then most of our team members are ZK and smart contract developers. So we build stuff very quickly. So sometimes we just build it too quickly, so that we just then we just deploy, to all the chains, and then to see, when there's more demand for certain chains and then more support from the foundation, we can just just bootstrap it pretty quickly.
My question with those chains for going there, is it because the functionality you believe is missing on Bitcoin that you would not be able to do these things on Bitcoin, or are you trying to capture some greater community and market share?
Yeah, sure. I think I can answer your question in 2 parts. First, definitely it's because on Bitcoin L1, you cannot do complicated, you cannot do trading, lending, and many complicated DeFi directly on Bitcoin, right? So that's one thing. So that's why we need to bring it to no matter Bitcoin L2 or all the existing other layer 1 blockchain or ETH L2. And the second is that there's actually a great product market fit for bringing Bitcoin to different ecosystems. We know that we've been talking with different foundations like Sui, say, Aptos, different ones. So they're all interested in having more Bitcoin liquidity and Bitcoin users to their chain. So that's exactly what they need. And then on the other hand, we also got. I have users who have deposited, who have minted 7 Fama BTC, in the past few weeks, and then he emailed me like, he actually hasn't known any bridge that could help bridge Bitcoin directly to EVM chains. So a lot of Bitcoin holders also have demand into doing more DeFi activity in other chains. Yeah.
As far as I know, for the BitVM to work, you need to be able to prove somehow the light client of the side system, right? How do you handle that if you have 11 different chain on the other side? Can you elaborate on that?
Yeah. So definitely we have light client on each chain so that we can verify each chain separately. So we can do, like, for instance, the EVM light client and smart contract code are audited by OpenZeppelin, and then we also have our Move VM smart contract for Aptos audited by BitLab.
But these are Bitcoin Lite clients you're talking about, right? Mm-hmm. But for the BitVM bridge to work, to peg out, you need to verify the consensus of Sui, of Eve, of Aptos. How do you handle that?
For that, we have our solution. I think it's maybe a question for our ZK developer to answer this question. Yeah.
Thank you. My question for Alex is, do you agree that Bitcoin is missing the functionality to do all of these different DeFi applications, and is that part of your mission with Arcade?
I mean, it's definitely missing a lot of pieces, but not only is it, I mean, if we were to have every soft fork available on layer 1 today, it would still not be a suitable environment to kind of execute, high throughput or sort of more advanced, sophisticated contracts. So you definitely need to elevate all of that activity off chain. Now the conversation, our opinion is that it gets a little harder if you're transferring that to another blockchain to kind of justify the security trade-offs that you're making, but also the potential scaling bottleneck that you're encountering. So we think that with Arcade, we have a solution where we can have something that's as close as Bitcoin as can be, especially even in terms of executing those contracts, where we take a little bit of liberty in terms of introducing, different script improvements to the Arcade off-chain environment, but those are still native Bitcoin. It's still native Bitcoin script, meaning that we don't have to introduce a brand new virtual machine. And there are upsides to doing that and leveraging the network effect of something like the EVM and whatnot. But I think almost kind of like the constraints of having to work within a Bitcoin script environment, but just having a little bit of options, a little more flexibility, will kind of invite builders to be a little more creative and perhaps come up with solutions to problems that haven't, because it feels sometimes like the EVM world has kind of like exhausted a lot of the upside in the open design space, whereas I think if we build something with Bitcoin that's a little more versatile, then it leaves a lot of space for people to come up with really cool new stuff.
And I think it's also Liquid is a living proof of that. Just adding new opcodes to Bitcoin is enough to build very complex DeFi primitives.
Yeah, exactly. I mean, but the problem I think with Liquid also was like at the execution level. Like it is true that theoretically, and Simplicity, which just launched, is going to be kind of an interesting experiment in terms of what people are able to build with the combination of opcodes on Liquid. But at the end of the day, you're still talking about a chain that has, I think, 1 minute blocks. And so if you're trying to do anything that requires fast execution, like DEXs, order books, or like even, I mean, comparing the environment of Liquid to any other ones in the industry at the moment, it's a little bit challenging to be able to attract liquidity because of these sort of like restraints on the conditions.
Thank you very much. I'd like to bring it back now over to Philip. Philip, you mentioned to me that all these things that make your application possible, a lot of them come from the expressivity of the EVM rather than Citrea's ZK magic itself. Would you be able to tell me one unique user experience that rollups and Citrea makes possible, and that's why you decided to build your application there?
Yeah, sure. There are many. I would just like to point out that I also agree that we should not mess with Bitcoin base chain, and then that's why we should have different execution environment to try out, experiment with different stuff. EVM works for us because we've seen the applications that have been building with VVM, and other ecosystems do really good things for user experience that we value. For example, passkeys and guardians are ones those that I mentioned. Limits are also really important. What we can do is play with it. It means like having something like streaming satoshis. Imagine that you are watching a podcast pops up a QR code, you scan it, and you're just providing the value back to the podcaster in the episode as it goes on. So this is just a random example, right? But I want to point out that the expressivity of it enables us to do stuff like that. While having a trust model that Citrea and ZK rollups enable, which can be enough in our case or can be enough for some users, right? So if they accept that, then they have a million possible solutions that they can do, like sessions and stuff on top of that. I think are really interesting as well. So yeah, providing this custodial user experience to non-custodial systems or systems that have a better trust model then custodial is something that we are really, passionate about, and we want to bring it live so that people can try out and see if that works for them.
Thank you. Adam, a little bird told me that rollups like Citrea and Alpen Labs, they need atomic labs quite a bit. They might even need them more than they need you. Could you elaborate a little bit more about that?
Yeah, that's correct. I mean, even the original BitVM paper states that the BitVM bridge, as it has its limitations of fixed deposit chunks, right? You can only go in with let's say 10 BTC increment. You can only go out with a 10 BTC increment. So this is not something that regular users or even institutions, for the matter, can easily use, right? So that's why a solution like ours is required. So we allow users to easily go in and out of these rollups for any amount. And we also do it quicker than the finality of the canonical bridge. And with our solution of atomic swaps with the light client, we also make it very good UX without liveness required. And we also make it pretty cheap because as we don't have any free option problem, it makes it possible that the rates from the liquidity providers are much better than for an HTLC swap.
Thank you.
I want to follow up on that. So for our BitVM bridge implementation, we don't have the fixed 10 BTC in and out limit because we have a local fungibility provider who can help user. For instance, the deposit only have 10, 1 BTC, amount, and then but the user want to withdraw let's say 2 BTC, then we can have fungibility provider to help you unlock 2, 1 BTC deposit so that the user can get 2 BTC. In one time. So that's a high-level overview of how we can enable a really fungible and flexible withdrawal amount, just like any other typical bridge.
Thank you, Yoavella. One user experience concern that I've heard about Arc that I would like you to address, Alex, is regarding refreshes of VTXOs on mobile devices, that the client must come online and refresh, and that requires people to open their phone, open the application, and then refresh their VTXO. Would you be able to talk a little bit about that situation, Alex, and ease our concerns?
I mean, sure. I think the liveness problem is something that applies to pretty much any scaling solution out there, whether it be with Lightning or even rollups. Like there are scenarios where a user might have to react to something that is happening on a security level to be able to, preserve the security of their funds. As far as Arc's concerned, there's quite a lot of ways to mitigate that problem. I think there's going to be continuous improvements to be able to assess whether that can be done in a sort of like background process way. But obviously, obviously, if your target market is entirely mobile users with perhaps kind of like unreliable connection, you're certainly going to have a hard time. So we built something at Arcade which we call delegates, which are a solution that allows you to have a bit of a watchtower-like sort of experience so that you can delegate the rollover of your VTXO into a new batch to a third-party provider, which might as well be the wallet that you're using, right? Obviously, this involves sort of like additional trust trade-off. You're effectively maintaining the off-chain status of your VTXO, meaning that you're still in the state chain trust model. But then when you come back online, then you can sort of like settle back yourself. But we also envision a scenario where Arc is used by a far sort of like wider cast of users than simply mobile wallet users. And so one of our main product at the moment is this full mine server that allows you to have a sort of like wallet daemon for LND Lightning operators, kind of like power users. These are people that are already running servers, and so there's obviously no liveness concerns from their perspective, and they're going to be able to settle in and out of batches in a very seamless way where it literally happens in the background in a coordinated process, making it so that we can even coordinate the moment at which a lot of them can participate in those batches so that they have the most cost-efficient settlement as possible, right? So there's a million solutions to this. Certainly, this is not something that's top of our mind when it comes to concern about the protocol.
Thank you very much. Now, just to wrap up, some closing words from each of our panelists today, starting with Yoavella, what you envision to be the ideal user experience for bringing Bitcoin to 1 billion users.
So it really needs to be like a Web2 experience. That's why we're building the Fama One app. User can easily do like 1 click, 2 clicks, so that they can borrow and earn on, all major blockchains. So that's, so we are not just focusing on the most trusted, secure infrastructure, but really like a Web2-like experience.
Thank you.
Yeah, I think the current problem with Bitcoin is that people have to choose between safety and self-custody. And then what we want to do is lower the barrier of self-custody enough so that people with a certain trust model access whatever functionality of the Bitcoin they want. And we hope that this will unlock access to Bitcoin and usage to much more people than we're having today.
Thank you.
So I think there is no size-fits-all solution, right? In the end, everyone will have to decide what kind of trust he is fine with. So there will be a huge range of solution ranging from stuff like eCash, Lightning, ARCs, rollups, maybe even other Bitcoin and other chains, right? And we just need to learn from Ethereum in this sense that we need to be able to each speak kind of the same language and be easily able to go between all these solutions. And this is something that Lightning Network is really good for, and something where if we come in, we can even provide something better than Lightning for inter-roll-up swaps, for example.
Thank you.
Yeah, I agree completely. I think the interoperability part is going to be key. It's possible that we settle on ideal solutions down the line, but it seems clearly that there's incentives and exploration being done for people to go in different ways. So as far as that's concerned, you want to have a system where you don't build wall gardens, right? Which is the principal thing. You want to have systems that regardless of the layer 2 you're using, is as censorship resistant as possible, so that the user does not end up being locked into that system. Because again, yes, you can swap in and out of it, but ideally, also, we think that it's important to have the ability to enforce your claim on chain, which is why we use very vanilla, so like pre-signed transaction. But these are a lot of concepts that hopefully we're not going to have to expose to users, and that they're going to just be using strict Bitcoin wallet with trust assumptions that they understand, but that is able to preserve the security of their funds.
Thank you very much to all the panelists for joining today. Thank you.
Thank you.
Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Gentlemen, some people have compared Bitcoin to a weapon, a gun. One thing I think we can all agree on is that Bitcoin needs good cryptography. And so here we have Liam Egan to talk Glock, garbled locks on Bitcoin, verifying proofs with garbled circuits. Please, a very, very warm welcome to the one, the only Liam Egan from Alpen Labs. Thank you.
Thank you. Thanks. Yeah, so I'm going to talk about Glock as a recent paper from me and the people at Alpen. This talk is going to be pretty high level, so if you want more details, I encourage you to check out the paper. I know there have been, and might still be, a bunch of talks about garbled circuits at this conference, so hopefully you're not all bored of them yet. But Yeah, so I'll just get into it. Yeah, like why do we care about this problem, right? Bitcoin is permissionless digital cash, or that's what I want it to be, and you know, it sort of, that was I think the original intention, but over time, I think it's failed to live up to this vision. And in part, this is because it lacks certain features that you might want from a permissionless digital cash system. It's not private, certainly not the L1, but in general it lacks, I think, state-of-the-art privacy. It's not expressible, which people have different opinions about, but as I'll say in a minute, I think this is relevant for kind of realizing the permissionless vision of Bitcoin. And it's not scalable. It doesn't work for, you know, everybody on Earth. And so I think we need to address these problems, you know, in order to realize the permissionless digital cash vision. Because of the lack of these features, in practice, many users, when using Bitcoin, rely on trusted third parties, trusted intermediaries. And this is bad for permissionlessness, because these intermediaries are empowered to enforce arbitrary rules. They're trusted, they can seize your Bitcoin, they can exclude you from the financial system, all of the things that the project was kind of intended to address. So because we don't have privacy and we don't have scalability, the future is uncertain, in my opinion. It harms fungibility, as we've seen. Bitcoin are distinguishable because they're not private, they can be seized, etc. So how can we like address these problems? You know, like other people are working on similar things, so maybe we could like try and think about how we could fix some of the stuff, like privacy or scalability. So one approach might be using smart contracts, but these are not possible with Bitcoin due to the limitations of Bitcoin script. You can't write very expressible smart contracts. And so maybe instead we could add some of these features via a layer 2. This is like a alternative system that sits on top of Bitcoin, but maybe settles the Bitcoin in a trustless way. In practice, the L2s that exist or have been proposed sort of partly solve these problems, and I think they have like a complicated set of trade-offs. Maybe they're trusted or have complicated liquidity requirements, or, you know, they can't, in my opinion, deliver all of the things that I want. So I think rollups strike an interesting balance in the L2 space. They offer like a compelling set of trade-offs where they're not centralizing, or they can be designed in ways that aren't centralizing and that don't require significant additional assumptions on the L2. They can kind of inherit the trust from the L1 as much as possible. And roll-up research has sort of happened largely outside of Bitcoin, but it's interesting that this problem can be reduced almost entirely to verifying what's called like a zero knowledge proof, or a snark on chain. And so people might have heard of snarks. They're like a way to prove that you know something without revealing what it is. They can be verified much more efficiently than verifying the thing directly. So you could have a program that checks that your L2 ran correctly and produce a proof that can be checked very, very efficiently. Unfortunately, Bitcoin cannot natively verify snarks on chain. This is not possible, and as a result, we can't really build like ZK type rollups natively on Bitcoin. So, what can we do instead? Can Can we verify snarks some other way? Kind of. So in Ethereum, for example, you would write a verifier for a snark and run it directly on L1. As I said, this is not possible in Bitcoin. Instead, what we can do is write a proof into the chain and allow people to prove that the proof is invalid. So you can provide a fraud proof that the prover is lying. And checking that something is invalid is often easier than proving that it is valid. So if a rollup sequencer, like the person running the rollup, puts an invalid proof on chain, we can actually design fraud proofs that are verifiable on Bitcoin today. And this is kind of called like an optimistic protocol. There are many types of optimistic protocols, yeah, this is one of them. I mean, it's kind of confusing because what I'm talking about here is like an optimistic ZK rollup instead of an optimistic rollup like you might hear about. It works differently, but the principle is the same. There's somebody who challenges fraud instead of proactively proving honesty. That's the sense in which it's optimistic. So most prominently, BitVM is like an optimistic type protocol. And over the last, I don't know, year, 2 years, there's been this effort to write snark verification in BitVM or BitVM 2. So how does BitVM work? The very, very high level is you can write a snark verifier that is just a gigantic Bitcoin script. It's too long and too complicated to run on chain. So instead, we can split it into pieces, and each of these pieces can be run on chain. If the piece, if you put an invalid snark on chain, then one of these pieces must fail. So we can construct a fraud proof by putting the piece of the verifier that failed on chain. So there's a few additional steps here. We have to somehow force the prover to link state between all of these pieces, which we can do using Lamport signatures. And we need to like kind of invert what the pieces do. Instead of checking something, they have to sort of prove that it doesn't work. But in principle, this is how it works. Yeah, and so this works. Like, I didn't mention, but like an alternative approach to trying to verify snarks on Bitcoin would be to add some kind of additional opcode. So most prominently, like opcat would allow us to verify certain kinds of proofs directly on chain. Unfortunately, it doesn't seem, it doesn't seem like this is going to happen. So the nice thing about BitVM and, as I'll say, garbled circuits is that they work on Bitcoin today without any changes. Kind of a strange model, but it's the best we know how to do right now. Yeah, so, and it's like relatively practical. It's like expensive, it's very complicated, but there's no like galactic constants that show up in the BitVM 2 style snark verifier protocols. However, it is expensive, like I said, right? You have to put a lot of intermediate states or commitments to intermediate states on chain, and you have to Lamport sign these states. And Lamport signatures are a type of signature that's verifiable on Bitcoin, but that's very large. So it like blows up this large amount of state to be significantly larger. And then the fraud proof is a giant Bitcoin script. So it's like 4 megabytes or something, which again adds even more data that you have to put on chain. So in parallel, about a year ago, a bunch of people sort of, I think, independently started investigating an alternative approach that kind of fits into the optimistic BitVM model based on garbled circuits. Jeremy Rubin was the first to publish this in a note called Delbrag. I was working on it. I think the Fairgate people were working on it, maybe others. So These garbled circuits are a type of cryptography, like another type of cryptographic primitive, like a snark or signature or something. And they're usually used in a very different context, in like multi-party computation. So, if me and you want to compute some function, like who has more money, we don't want to reveal how much money we have. We can do this using garbled circuits and keep our amounts private and only learn 1 bit, say. That's the usual context in which they're presented. Here, we're using them in a very different way, basically to replace BitVM. So a garbled circuit protocol has two parties, a garbler and an evaluator, that sort of do what they sound like. The garbler takes a circuit and garbles it. So you have a circuit, and you put it into this sort of encrypted form where the evaluator can run the circuit, but can't necessarily learn anything about what the circuit is doing, and is able to produce a proof of integrity, so like that they ran the circuit correctly. If you just sort of ask them to run the circuit, maybe they would cheat, right? Garbled circuits prevent that, and that's the property that we care about for our protocols. So during setup, the garbler sends this garbled circuit to the evaluator. You can imagine the garbler being the prover and the evaluator being the verifier in these kind of snark verification protocols. Then, during evaluation, the garbler will encode a proof, an input to this circuit. So imagine the circuit is a snark verifier, it's checking a proof. The input is a snark, and by encode, I mean Lamport sign. So they're going to kind of sign this proof. This binds the garbler to the input and also prevents a malicious evaluator from providing a different invalid input. So it kind of gets us both properties, that the garbler is bound to it and that the evaluator can't substitute something else from the garbler. So given the input, the evaluator uses the garbled circuit to derive an encoded output. Again, by encoded I mean Lamport signed. So one way to think about what the evaluator is doing here is it's kind of like evaluating a function on signed data. So you sign something, and normally I can't do anything with that. But with a garbled circuit, I can evaluate a function on the signed data and preserve your signature. So now you have assigned the input, and I can get a signature on the output. So if you sign an input that is invalid, I can obtain a signature that it is invalid. So I can transform the signature into this secret, which is just like a big number or something. So if C is a snark verifier, W is a snark, it outputs 0 if the snark is invalid. I learn this secret S0 in that case. If the snark is valid, I learn S1. So if I know S0, it means you must have signed an invalid snark. So S0 is like a fraud proof. If you sign an invalid snark, I learn S0, and that I can only learn S0 if you sign an invalid snark. And so maybe you can imagine how we were going to use this, because we're going to use this mechanism to replace BitVM. So remember, in BitVM, we had a big program, we split it into pieces, and you run a little piece on Bitcoin to prove that you had an invalid state transition. Here, it sort of works very differently, but the interface is kind of the same. You sign an input, and then I can derive a secret if your input is invalid, if you provide the wrong kind of input. So the garbler is the prover, and the evaluator is the verifier, as I said. And the garbler will encode, as in Lamport sign, a proof, put it on chain, which is the same as BitVM. In contrast to BitVM, the garbler, the prover, does not put anything else on chain. They don't commit to any intermediate states. It's just this input. So already there we have a fairly substantial savings. Then the evaluator uses the garbled circuit, as I described before, to derive a secret. This secret is corresponding to whether or not the proof is valid or the proof is invalid. And then, if I learn the secret that corresponds to the proof being invalid, I can put that on chain. So I could reveal a hash preimage, or I could produce a signature. You can sort of design these protocols in different ways. But if I know this secret, you must have put an invalid proof on chain. And so that by itself is a fraud proof. A single signature is a fraud proof. I can prove that you signed an invalid snark with just one signature. So here we save that big fragment of Bitcoin script I talked about with BitVM2. We don't put that on chain at all. Yeah, and so overall, I think this saves roughly like 500x the data on chain compared to BitVM2. There are, of course, lots of different parameters and ways you could design these systems, but for like a snark verification program, I think that's the number. What's the problem with garbled circuits, right? If they're so obviously better, why didn't people use them already? So in the garbled circuit paradigm, the on-chain costs are very low. You don't have this big program on-chain, you don't assign intermediate states, but you do have to generate a garbled circuit. And the garbled circuit is very large. It's so the original approach that I considered and that the BitVM Alliance has pursued is to try and garble a Groth16 verifier. And I think from Ekram's talk, the Groth16 verifier has about 2 billion AND gates and 7 billion XOR gates. Each of these AND gates involves cryptographic operations and is about 16 bytes. So we're talking about a fairly large amount of data. And then each of these garbled circuits, when you want to use this in practice to build a bridge, you're going to have one maybe per pair of watchtower and operator, or even like per deposit, depending on how you design things. So the costs very, very quickly explode out of control. And those numbers are the result of many like months of working on this problem. So it was not obvious, I think, in the beginning that the garbled circuit approach would be practical. And so we propose an alternative scheme that we called Glock 25. So Glock is like a term that we use to refer to these kinds of garbled circuit type protocols. And Glock 25 is a specific instantiation of this scheme. So we, by GC here, I mean like Glock. It's actually like a fairly standard garbling technique. But we propose a new type of snark. So I said that the Alliance is garbling a Groth16 proof. We are garbling a modified version of a different snark called Parry, which was published last year. And it may be of independent interest that our snark, I believe, is the smallest known snark, which is kind of cool. Because we use this different type of snark, we're able to instantiate it as a designated verifier snark. So a snark, like is a proof, right? There's a prover and a verifier. Typically, the verifier can be anybody. A designated verifier snark, the verifier must be a specific person. Or another way of saying this is that the key that you need to verify the snark involves some secret information that the prover cannot know. So by instantiating our snark as a designated verifier snark, we're able to dramatically simplify the verification circuit. Instead of using pairings, as Groth16 does, and pairing-friendly curves, we are able to use any elliptic curve. In particular, somewhat controversially, in the paper we propose using a binary elliptic curve. And this binary elliptic curve is really interesting because it arithmetizes very nicely into a garbled circuit. So I don't want to bore people with all of the details of this, but if you're interested, find me or check out the paper. I think it's pretty neat. On the whole, though, we're able to reduce the number of AND gates from, I think, like 2 billion to something like 12 million. So it's a very, very substantial reduction in the complexity of the verifier circuit. And our garbling table can be as small as like 160, 180 megabytes. And this is quite a bit smaller than other approaches. So there are trade-offs, like these design decisions are sort of inspired by our application, which is building a bridge, as I sort of talked about at the beginning, to a roll-up. And this designated verifier assumption is acceptable because of other constraints that come from the rollup. In particular, that the sort of challenging mechanism for fraud from a sequencer must be permissioned, or at least as far as I'm aware, nobody knows how to do it in a way that is not permissioned for the heaviest chain. And therefore, it is acceptable to have a permissioned verifier. That's sort of what a designated verifier is. You could imagine it being like a permissioned person. Yeah, and so we propose a bunch of other interesting optimizations, I think, in the paper. In particular, something I haven't really addressed is a bit of a sort of detail of garbled circuits, is that we have to ensure that the garbler is behaving honestly. So when I'm garbling a circuit, I send you this giant piece of data. How do you know that it actually is a valid garbling table? If it wasn't, then when the evaluator goes to evaluate the circuit, they might fail. And if they fail, they will fail to derive a secret in the case of fraud, which means the protocol is insecure. So we have to ensure that the garbler cannot send, with high probability, an invalid garbling table. There are several approaches to this. One of them from Jeremy is called grug, which uses a Bitcoin script to check each gate. This, I think, is practical. I'm not sure, but it incurs very, very high costs, and in particular, it does not get rid of the kind of BitVM style proof on chain, or script on chain, I should say. Another approach would be to use a snark to prove the garbling is correct. This is not practical right now. Maybe it will be in the future. But then the third approach, which is what everybody's doing, is called cut and choose. So you take your garbling table and you basically garble it many times, and then the evaluator chooses half of them to check, and then a different half to open at evaluation time. And so long as one of the ones that they have opened at evaluation time is valid, the scheme is secure. We use cut and choose, as does the Groth 16 approach, and we have some interesting tricks to make this work nicely with Bitcoin to keep the costs on chain very low, using verifiable secret sharing and adapter signatures, which I would encourage people to check out. It's yeah, maybe a bit much for this, but anyway, so looking forward, I think that the garbled circuit paradigm is just sort of starting out. There's a lot of really interesting design space on a number of different fronts that is yet to be explored and will, in my opinion, yield a lot of really are much better protocols than we have now. So I think Glock is an example of this. By changing our perspective on the snark, we're able to get much smaller garbling tables. Maybe by investigating the garbled circuits literature more, we can use better garbling schemes. There are arithmetic garbling schemes. There are different schemes for malicious security. Perhaps we can even use garbled circuits in the bridge protocol in other more interesting ways that don't involve snark verification. I think that this is a really interesting application, and I don't know. I mean, I have this kind of take that snarks went from a very theoretical kind of cryptographic construct to very, very practical. There are ZKVMs that you can use today to prove programs in the span of 10-ish years. And this is uncommon in cryptography, I think. And the reason why is because snarks found their perfect application in blockchains, in particular in Zcash and private payments. And this kicked off a cycle of research and development that just very rapidly uncovered this huge practical space of protocols that otherwise people probably wouldn't have thought about, because academics are maybe not interested in these kinds of applied questions, and engineers are not going to just like try random cryptographic protocols to see if they're practical. I think that this application of like snarks on Bitcoin and bridging can do the same thing for garbled circuits and for other kinds of cryptography. So for example, like Weiking has proposed using attribute-based encryption. This is not practical today, but if people care about this enough for this application, maybe we can figure out how to make it practical. And the key missing piece for snarks was finding users who would tolerate like really inefficient protocols. And so if you want private internet money, it's your only choice. If you want Bitcoin bridging without some kind of soft fork, this is basically your only choice. So anyway, that's my take on this. And that's why I think it's like an interesting research and applied problem. Yeah, so alternative garbling schemes. I expect things to look very different in the future in this space, and I'm very optimistic that we can do a lot better than we can right now. And that's it. That's all I have. Thanks.
Okay, guys, any questions?
Thank you for the talk. Do you think we can get this bridging permissionless?
Permissionless? They're different. So, I think there are a few ways that it could become permissionless. Like, and I don't think permissionless is maybe best conceived of in like a binary way. Things can become more or less permissionless. So we can certainly make things more permissionless. Like, I think that's probably very feasible. For example, in BitVM 2, challenging for the validity of the snark is permissionless. Anybody can do it. In the current like Glock garbled circuit type protocols, it is not. This is a limitation, I think, of the garbling schemes and like also to some extent the protocols. But I think we can definitely do that. So there are other things though that are much harder. For example, in all of these protocols, we have to simulate covenants using a signing set. If we hold Bitcoin constant and don't add any covenants, I think this is extremely difficult to work around and perhaps not likely to be possible. I will add, just as like an interesting note, there are cryptographic primitives that if they existed, we could use to simulate covenants and to do all of these things in a more permissionless way. In particular, indistinguishability obfuscation and functional encryption would allow for this. You can kind of build like a little cryptographic computer that you can't introspect or manipulate. It can just, it's like a perfect black box. It's not exactly, but it's you can sort of think of it like that. If we had these technologies, then yeah, you probably could build almost entirely permissionless bridging protocols. However, I wouldn't like hold your breath for that, you know, maybe, but.
Hey, Liam. So in terms of the trade-off of BitVM 2 and Garbled circuit, so what advantage Garbled circuits have that make Alpen and the whole BitVM alliance think that, okay, pivoting to Garbled circuit is worthwhile?
Yeah. So I think the main thing is on-chain costs. We're not putting a lot of intermediate state commitments on chain. We're not putting a big slashing script on chain. As I said, we're going to reduce the on-chain costs by like 500x. So this has a lot of positive downstream effects on the economics of the bridge, and like it's just very desirable. Now, the main trade-off of garbled circuits is the permissionless evaluation or challenging. We think this is acceptable because in the sort of BitVM paradigm, you have kind of two things that you can challenge for. You can challenge for an invalid proof, and you can challenge for a proof about the wrong thing. BitVM 2 allows for challenging an invalid proof permissionlessly. Challenging the wrong, like the thing you're making the proof about, say the heaviest chain, is not known. Like, we don't know how to make that kind of challenging permissionless. So overall, the system has permissions challenging. So we think it's okay to make challenging for the proof validity permissioned. But I mean, all else being equal, it'd be great if we could avoid that. But that's how I think about the trade-off space. There's also like engineering benefits and modularity, and so, but yeah, that's the main thing.
Unless we have no further questions, we'll just thank you, Liam Egan, again for his talk. Thank you, Liam.
Thank you.
Ladies and gentlemen, up next, we have a break before the hackathon final presentations, which will begin at 5 o'clock. So you have a break for the next 37 minutes or so. The hackathon final presentations will take place here on the main stage at 5 o'clock. Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin plus scaling edition. September 3rd.
Teams are here to present for you today on stage. So teams will have 5 minutes to present. Judges may ask a couple of questions, and that will be it. So, yeah, are we good to go? Yes, we're all set. For Hackathon teams presenting, take a look at the order that you're presenting that we sent in the Telegram. When the team before you is presenting, just come up close to the judges booth, just so we can keep the transitions between teams quick. So yeah, take a look at the list. Right now, the first team is going. If you're second, come up and sit close to the sound booth. Awesome, thank you.
All right, I guess I start. Hi everyone, I'm Maru, also known as Maru Mover online. I've had the pleasure. I am. Oh, that's not meant to be. Okay, not yet. It's fine like that. No. Lost my train of thought. Okay. Yeah, I had the pleasure to learn about the different solutions that are sprouting in the ARC protocol. And given my interest in privacy-preserving technologies, I wanted to build a privacy-focused app that will encourage users to participate in ARC. Introducing Raki Wallet. Full disclosure, this is my first time building a wallet by myself. This is not a team, it was a solo effort. And yeah, so I use Replit to build the front end of this React Native wallet, and I use Expo to mock it. I also want to say, for context, I have limited knowledge on the ARC protocol, so thank you so much, ARC Labs and Second, for your documentation that helped me frame my concept. So Raki Wallet is meant to be a user-friendly wallet that has privacy features. Let's go through the application features. So in this wallet, you'll be able to onboard into ARC from Bitcoin. You'll be able to exit from ARC to Bitcoin, and you'll be able to transact privately within ARC. The first screen shows the boarding aspect that gives like an overview of the boarding process, and so that the users can see. Given the nature of the protocol, the UTXOs that are converted into VTXOs have an expiration date, so I wanted to also include in the wallet an easy way for the user to be able to refresh the VTXO before it expires so they don't lose access to their funds, and that's included in the app design. Now, the most important aspect of this wallet is the privacy aspect, and the way that it would work is from the back end, which was not built, is how I envision it. As I understand the ARC protocol, the ARC operators are the ones that are essentially fronting the liquidity for the transactions that are batched in rounds. And in this process, when they're receiving the VTXOs from the users, they're also asking the users to sign a forfeiting transaction. In essence, the ARC operator is able to see all the details of the VTXO transactions, as well as gaining control over the old VTXO in the forfeiting process. So how the smart contract would work, in the concept is that it would interact with the ARC protocol, and it would define like witness vectors, the round one constraints, in order to be able to use snark proofs so that the ARC operators can validate faster and they don't have to gain information into all details of the VTXOs. Often we know that this process is complicated, even though it's fast, but often users are lost in like where they stand. So I wanted to make sure that the sending Raki, as I call it, you can see where they stand in the process for this smart contract interaction with the ARC protocol. And that was basically all I was able to do in 3 hours. I would have liked to be able to build a test environment where I could interact with a mock ARC operator to test the logic, but I didn't have time for that. And if anybody here is interested in the concept and would like to work with me, you can reach me at MaruMover, or you can comment on the dev post. I would love to engage with those that have more knowledge than me in creating these types of smart contracts in ARC. Thank you.
Great job, Rocky Wallet. Judges, questions?
Hi, yes, love Rocky Wallet. I think one of the questions we were asking you yesterday, and one of the things you said you were going to try to do in the interim since we last spoke was, I think the biggest question I had and some other people that didn't quite understand, we don't quite understand ARC or exactly what you were trying to do, was to confirm whether or not the ARC protocol can do what it needs to do with the kind of zero-knowledge obfuscation that you were wanting to do. And I'm wondering, did you have time to talk to some ARC people and get a better idea of whether or not it would be possible to do this kind of obfuscation and to have the ARC protocol work the way it needs to?
Yeah, I had a chance to ask Brock, one of the creators of the ARC protocol, about it. He mentioned that, yes, it would be ideal if this was done at the protocol level instead of the application level, but it could be done with a smart contract that interacts with the protocol. The specificity of the smart contract, we were kind of discussing it and didn't get a chance to finish it, but I was even brainstorming maybe if there's some sort of escrow embedded in the smart contract so that the ARC operator is incentivized to sign for the batch round despite not having without the batch operator needing to front the money. So we were brainstorming.
Perfect. It sounds like Barak is saying that it's probably possible to grow a functional back end for this front end.
Yes.
So that's cool. Thank you.
Awesome. Great job, Rocky Wallet. Core LLM, you are up next. ZK Poor, you are on deck.
Testing. Is this microphone share? Yeah. Okay. When you're ready. Go ahead.
Okay. Thank you, everyone, for being here for our presentation. Today we are presenting Core LLM. The idea for this project comes from what we think is an issue in open source development, which is onboarding new developers to an open source project. Onboarding a new user, more than a new user, a new developer means that you have to follow the new developer with all setup of the whole environment, explaining the code, explaining what is going on, etc. This is a huge effort and a huge loss of time for, let's say, senior developer. And so we thought of this, and now Matthew is going to explain what it is, to help onboarding new people to open source project and to increase, let's say, efficiency in the process.
Thank you, Tuma. So what we have is we have an LLM that looks directly at a code base. And what it will do is rather than fetch information from the internet, it goes directly into the code, inspects it, and then answers whatever questions you have with specific references to the files and the lines. So right here, I took a few samples of the most esoteric and poorly documented aspects of Bitcoin Core, such as lib-mini-sketch, and then also net group bucketing and ASM maps. If any of the judges have any suggestions for a query that we can run, we can do in real time right now for the audience. Oh. there's one at the back, Hunter Beast.
Ask it about CS main.
How do you spell it? CS?
Main, M-A-I-N.
Okay. Here, hold this. So right now it's going and examining the code base, it's thinking. So the first step is that we have locally on the machine, it goes through all the files to find what matches with it, and then that will construct a package of data that gets sent off to the Claude API, which will return a response that is very detailed explanation in simple English about what we're looking at. Recently, I was in Amsterdam at the 2140 office, and I was told there that there is a serious problem with PR review in Bitcoin and going through what PRs need to be merged and having people go through all that code. So this could also really advance and accelerate that process and be used immediately. So here's the answer about CS main. We can see where CS main is in action in the validation.cpp file. You can see CS main is being used to protect the transaction validation process. So how CS main protects the mempool, and we can see the specific file name and the specific code in question. So, yeah. Thank you. We have time for more queries. Go ahead, Super Testnet.
Are you familiar with DeepWiki? And if so, what would you say are some improvements that yours has on DeepWiki?
So something about DeepWiki is that it works on existing code bases that have been submitted for review. With our project, what we can do is you can take a code base and just put it real time into the directory in which the LLM program lives, and then you can query any code base that's actively in development. You can run this locally on your own machine, and you don't have to wait for a submission to an existing website process. Yeah. So it could be self-hosted on your local machine and so on.
Yeah, another cool stuff is that you can really take any code base from a private or public project, you name one, and you can give it directly to the LLM, and it will help onboard new developers or do PRs for every single project it comes to mind.
Thank you.
Great job, Core LLM. ZK Poor, you're up next. I just got a text from Abdel and said that he is on his way, so feel free to take 30 seconds getting set up before. Yeah, let's actually switch the order. That makes way more sense. Merge Sync Pi, you are up next if you are good to go. Oh, actually, just kidding. Merge Sync Pi, you can still... Merge Sync Pi, you are up next. ZK Poor, you are now on deck. Yep, go for it.
Okay, thanks for coming. Today I'm going to present Merge Sync Pi. Big disclaimer, friend, 99% of the stuff I showed you, I was actually working on a project the last 3 months. The only thing I've been doing during the hackathon is the Pi part. So what merge sync does is basically it is a new method that uses MapReduce and tries to do IBD a lot faster because the blockchain has been growing. We used to be at 4 gigabyte after the first halving, and then we've been increasing ever since. Today I'm going to try to do basically have a race between Bitcoin Core and merge sync on a Pi. Merge sync is going to run on a Pi, and Bitcoin Core is going to run on my MacBook. And let's try to set it up. So 1 second. Okay. So I'm going to connect to it. Hopefully it works. Okay, good. So here's the Pi, just to show. It's connected via wire, and I'm going to cd into the right directory. And then I'm going to time this one. And okay, here we're gonna run simply top to see how many CPUs are running, and here on this, yes, and here we're gonna run. So we're gonna run Bitcoin Core, and we're gonna time it. We're not gonna connect, and we're gonna do a stop at height, also the same height. Okay, let's start. So both are running now, and as you can see, the Pi is also busy working. And I'm going to talk quickly about how it works. So we're trying to process the blockchain, get the UTXO set, the chain's growing, and IBD is taking too long. So because mostly we're processing sequentially, and so it's basically like adding disks into your installing Windows 95 one disk at a time, right? It's not very fast. So instead, what we're going to do is we're basically going to have extract the blocks, and we can do this perfectly in parallel. So we're going to start with the out points, first one, and then the blue one, the other blues, and then the orange, then the greens. So very, very simple, okay? Basically imagine like colored book on the bookshelf. And we do this for the blocks before and after as well. And we don't forget about the orange one. That was basically on the Coinbase created. And now all we're going to do is simply sort. So who can sort a rainbow? Oh, we're going to start with red, and then there's no red. Okay, what's next? Right, yellow. So and then orange, and then we have another orange there, and then we take green, another shade of green, then the blues, and then and finally the final pink. And now all we have to do is basically after we sort it, we basically just need to eliminate the duplicates. That's basically the spending of the outputs. And we identify them. That's very quickly because it's basically just a simple memory walk. And okay, that's done. And now we compact it, and that's basically it. Let's see if we finished. Okay, so the Pi finished in 53 seconds, and the Bitcoin Core finished in 1 minute and 4. So we were slightly faster with merge sync on the Pi versus a MacBook. Yes. Any more questions? I have no idea. Usually it runs twice as fast. Maybe I have the Pi is too hot or something.
I wanted to ask, any idea how long it would have taken with Bitcoin Core on the Pi?
Yes, it would take 2 minutes. I did a test. The same thing would take 2 minutes. And usually, I don't know why it didn't this time. And during the hackathon, it worked in 25 seconds. Now on stage, it worked. It took 1 minute. And yeah, so it's roughly 4 times faster. But it really depends on how many cores you have and how fast your I/O is. And yes. So yeah, just basically we're sorting bookshelves by color. That's the idea.
Yeah. Can you talk about the challenges, if any, that you had importing this thing that you had prior to this hackathon to a Raspberry Pi?
Yes, well, it's the very old developer scheme. Like, it works on my machine, and I was only working on my laptop for the last 3 months, and it worked fine. And luckily, I was using Rust for most of it, so it was actually a lot less work than I thought. It wasn't compiling at first, but then I just basically said to type the compiler errors into Claude or GPT-5 and say fix this, and then after 15 minutes or so, it was running. So Alex almost, I didn't want to do it because I had to prepare my slides for the actual talk, and then Alex convinced me to actually do it, and because in my mind was like, okay, either this is going to take 30 minutes or 3 days. There's no way anything in between, right? And yeah, luckily it was the faster. So
okay, perfect. Thank you.
Great job, Emerging Spy. ZK you are up next. Artmock, you are on deck.
Check, test. Hey. Hi, how are you? Nice. Can you hear me? Yes? Okay. Hi everyone. So the project is ZK Pro, zero knowledge proof of outstanding reserves. And the goal is simple. The goal is to end the Bitcoin paper season using star proofs. So yeah, we were all happy when Bitcoin was above 100K. Everyone was happy, and the corporate treasuries were saying, yes, we totally have the Bitcoin, trust us, bro, it's fine. And the Bitcoiners said, show us the sats. And they said that the best they can do is a PDF. And of course, we are not happy because we are cypherpunks. So we want to do better. And yeah, Michael Saylor was saying, oh, but we don't want to disclose our addresses because we don't want to become a honeypot. So they were trying to use those security reasons to not disclose their holdings. And then the result is that no one knows if they actually have the Bitcoin they claim. And yeah, what would Satoshi do? We believe he would want to use cryptographic proofs. And basically, the goal would be to be able to prove that you own a certain amount without disclosing anything about your addresses or your transaction history and stuff like that. So the flow is the following. The idea is that the treasury manager would input a list of UTXO, and then you will generate a proof of the ownership of those UTXOs and the sum, the amount that they represent. And then anyone could verify the proof. Yeah, so this is what I said. And then basically everyone is happy because there is transparency, and then you can imagine to actually verify the proof anywhere. And yeah, so I will show you an example of the demo. So this is what we did. So it's a fork of the Bitcoin Treasury dashboard that Jack Dorsey company made, the block one, and we just added those two functions. So we actually don't generate the proof in the browser. We generate it in a Google Cloud instance that is here. We actually were not able to generate the full proof of the ownership of UTXOs. We just managed to generate the proof of the header chain. And the reason is that we are doing the verification of UTXOs in a naive way, which we have to iterate over the blocks and to check all transactions to see if the UTXO have not been spent. And because we have to do a lot of SHA-256, it's a bottleneck in our proving system. And we had to do that with recent blocks on mainnet, and there were about 3,000 transactions at this time, so we are not able to generate the proof. But we know how to do it in a clean way, which will be to use U3XO, and then it becomes easy to prove. So the generation of the proof here will be fake, but it's just to illustrate the flow. For the treasury manager, he would input the list of UTXO. So those are real UTXO from mainnet, and then you will generate the proof. And you could also generate the proof in the browser. It's just that it will take longer. So yeah, and then once you have the proof, anyone can verify the proof directly in the browser because we have WASM verifier of the Stark proof. So that you can do it in the browser. Yeah. So, as I said, for companies, they can prove reserves without security problems, without disclosing their addresses, and it gives more confidence maybe for their investors and everyone. And also, it's a good way to preserve the Bitcoin culture of not trusting anyone and being able to verify everything, and here in a privacy preserving manner. Yeah. So that I said, okay. So what we built during the hackathon, so we did the fork of the UI UX, adding those features to show how you can have the full flow end to end. We did the Cairo program for verifying the UTXOs, but as I said, we did it in a naive way, which is not efficient. This is why we were not able to actually generate the proof. We did the Rust backend with the proof generation, and almost the stock verification in the browser, we were not able to finish it. There was also something that we learned, an interesting question for someone who was asking, okay, but if someone has a proof, he could also claim that he owns the UTXO. And then we found a simple way to do that. In addition to the UTXO list, you will also add a public key. And then you can sign a message off-chain to show that actually the proof was generated by you. So it's something that is easy to solve. Yeah, that's it.
Great job, ZK Poor. Judges, questions?
Maybe I'm showing my ignorance of proof systems, but does the proof include a proof of spend? So like if basically like any of the UTXOs in the proof, it also, it's, what do you call it? It proves that they can also spend it, if that makes sense.
Yeah, so basically, what we do is that we can prove that UTXO has not been spent, but there is a notion of freshness because we cannot do that indefinitely because it can be spent later. So you could have some mechanism where you can have a proof that at least during the last week it was not spent or something like that. So you could continuously generate new proofs to prove that you still own them, something like that.
I meant more that it's proof that they can't pick any random UTXOs. They have to include proof that...
I didn't mention that. Good point. Yeah, we did not actually verify the ownership of the UTXOs. But this is something simple, again, to do. We could sign just some arbitrary message for the public key associated with the UTXO. Oh, yeah, and we did that only for pay to public key hash for this, because this is a simple case. But we could also do that for other types. Yeah.
Thank you.
Great job, ZK Poor. Artmock, you are up next.
Test, test. Okay. Let's see if I can get an HDMI going in here. Yeah, I know. I'm just, you know, thinking about other stuff, like getting my slides positioned on screen and other worthless endeavors. USB hub, do I want it to connect? Yes. All right, cool. I think we're good here. Okay, cool. So my name's Steven. This project is called Artmak. This is a word that comes from Ottoman Turkish that means to grow, become more, multiply, remain over, be left. I'm not Turkish, but that's what ChatGPT and Wiktionary said. So here we are. The reason I wanted to choose a Turkish word that meant something to that effect was that we're at a conference here in Turkey talking about scaling, and a lot of different solutions, ZK stuff, Arc. The one that I've been kind of particularly interested in is the Arc protocol. And I wanted to kind of ask the question with my project, how scalable is Arc? Because as someone who works a lot more on Lightning projects, I tend to struggle with stuff like Lightning liquidity and the kind of liveness requirements of Lightning and all that. So I wanted to see, like, does Arc allow me to onboard users quicker? Can I onboard more users with less liquidity, and will it work for small payments, and will it work quickly? So how scalable is Arc exactly? Well, let's find out. So that's why I made Artmak, and this is a Bitcoin Arc wallet implemented as digital performance art. So let's see what we're going to do. Let's take a look at it right here. I have it open in my browser window here. You can see I've got like my little buddy on screen. He's got 10,000 Bitcoin in his Arc wallet. I'm going to grab a boarding address and just give him a little bit more Bitcoin. So I'm going to go to my Voltage Payments wallet, make another payment, come on. And we are going to, let's see how far we can push Voltage. I'm just going to send 100,000 sats of Mutiny Net Bitcoin. And it's going to, take a little bit because it's got to go on chain. But in just a second, we should see some of that come up here in the balance here so that we can actually board the Arc. Cool. Yes, so it left the Voltage Payments wallet. Okay, so in a little bit, this guy is going to get some more Bitcoin. Now, what I'm going to do here while we're waiting for that Bitcoin to arrive is I'm going to go to my phone, and I actually have the same website pulled up, and so this is me actually controlling another character from my phone, and this character has his own Arc wallet, and I'm going to actually send some Bitcoin to this other character by, where'd my mouse go? There we go. I'm going to actually click on this other character, and then boom, I sent 1,000 sats to this other character now. And I can click again, and I can send more sats. And so basically, the more sats you send, the smaller you get, and the faster you can move across the screen. Oh, hey, our 100,000 sats arrived. Let's board the Arc. So I'm going to board that, and this is going to, like, as I understand it, there's going to be like an on-chain transaction. It's actually going to create a VTX or whatever. Now I'm huge. As you can see, I'm stuck at the bottom of the screen, and I've gotten so fat with all the Bitcoin I have that I can't move fast. So what I want to invite everybody to do now is to join the game with me. So if you scan this QR code, you can actually join the game. Or if you type in the address, it's better at widescreen on your laptop. This is like Xbox 720, like HD graphics. You're going to want to see this. Oh, wow, look at these people. I'm going to send them some Bitcoin. I'm going to send that one 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 Bitcoin. These are all real Arc payments, by the way. All of you now have an Arc wallet on your phone now. So I'm just going to get rid of all my Bitcoin. And if you don't want to be slow and fat, you're going to try and run from me so that, look at all those Arc payments. Wow, maybe Arc is scalable. Holy crap, whoa. I'm just curious. I'm probably stacking up tons of VTXOs in my browser. Like, this is insane. Like, I bet if we went into Dev Console, we'd see, like, yeah, it's like checking the balance and all that kind of stuff. And man, there's a lot of VTXOs here. But yeah, so I guess people are closing their phones and they're leaving the game, probably because it's pretty buggy. But you get the point. So feel free to keep playing around with that and mess around with that as long as you want. Send each other some sats on Arc. You can withdraw it. You might be able to withdraw it if we put a Lightning withdrawal in. So this was built with the Arcade OS SDK to handle the Arc stuff. The kind of web app is TypeScript, React. So there is a client package, which is the like pretty website thing that you were looking at on your phone. That's on Netlify, and then we use Render to host the game server backend, which coordinates the like state updates, like which player has which location. It also is used to send to the Arc wallet so that you can like always know how to pay by tapping on that player. So yeah, that's basically it. You can find my source there, and that's what I got. Any questions?
Super fun. How would you improve the game mechanics?
I'd improve the game mechanics by adding some kind of boss character that eats you, and if you are too slow, then you'll get eaten. And so you need to find a balance between being fast enough to escape the final boss, but still having enough Bitcoin. And then there ideally should be something that allows you to like withdraw sats or something, or win a jackpot or something like that.
Great job, Artmock. Up next is Bridgester. Bridgester, you're up next.
Yeah. All right. Yeah, exactly, please. All right. I made, with the help of a small team, app called Bridgester. It is a Bitcoin node to Nostr relay mempool bridge. It's designed to take all of the unconfirmed transactions out of a Bitcoin node and publish them to a Nostr relay. Made a Nostr kind 25,000 to represent Bitcoin transactions. I don't feel like I'm on. There we go. So it will pull unconfirmed transactions out of a mempool. It will post them to the Nostr relay as kind 25,000 events, and it will take any new events that it sees and send them to the Bitcoin node. So you can post a raw transaction to Nostr and expect it to hit a Bitcoin mempool at some point. And same thing, if it's not making it out of the node, your peers aren't accepting the transaction, you can get it to Nostr where it might find another peer who will take it. Some of the benefits of this, you can't have time-locked transactions in the mempool, so you could actually post your time-locked transactions to a Nostr relay, and once they are validated, once they are valid in mempools, they can get absorbed into a Bitcoin node's mempool and then propagated around the network. This is all vibe-coded slop. I started in bolt.new and rapidly ran into some difficulty with that application, so I moved over to Replit, and most of this was built in Replit. You can see I assume it's working app at bridgester.replit.app. We have a wallet that should show a balance, but currently doesn't. A way to mine blocks. We made a button to publish it to BitChat, but obviously that looks like it doesn't do anything. The idea there being, if you were on a plane with 5 other people, one of them could buy internet, and you could post your transaction into BitChat, and they could post it to Nostr for you through their internet connection. So that would be neat if that actually worked. You could put in recipient addresses, amounts, and a message and send it on to Nostr. At one point during my 3-hour fighting with robots to make this work, it actually did the thing, or it said that it did the thing. I did have the ability to mine blocks. It would show me the block height. It would show me the wallet amount. And then I have this verification tab that would shows that it is disconnected right now, so obviously nothing's working. I asked the robot to add a Stark proof verification to make sure that the transaction submitted to the Nostr relay is a valid Bitcoin transaction, and it said it did it. I have no way to prove it. I don't know what a valid Stark verification looks like. But there was at one point a button that would pop up and say verified. These two empty windows used to show all of the transactions that were submitted, and there was a button where you could go and view those transactions on nostr.band. Now, never actually saw any of my transactions there, but 3 hours is not a lot of time to make things work fighting with robots. And then I asked it to tell me how it made this application, and it made me this tab. So here's the tech stack. I am assuming that it actually used these technologies. I have no real way of verifying because I am not a dev. But there's a lot of things in here that it did, and it seems like it did some of them right, and maybe I could spend more time to make them actually work. So there's that. There's, this is also vibe-coded slop. I did not give it a lot of information. It just pulled it all out of itself. But it does represent all of the things that I wanted to do with this project. So instead of just reading out all of this stuff that it wrote, I'm just going to click through the pages. How much time do I have left? 30 seconds. All right, I'm ending early. This is Bridgester.
Great job, Bridgester. Judges, questions?
Xfrog, I'm just curious, like how much, if any, kind of programming knowledge or experience you had before this.
Back in the late 90s, I learned some HTML and CSS.
Got it. That's
Yeah.
cool.
Yeah.
It's impressive that you got this much. That's pretty cool.
I can open a terminal window and do hello world.
Yeah.
Cool. A couple different languages, but
it makes this more impressive.
Yeah, thank you.
Great job, Bridgester. Another round of applause to all our finalists. All right, there's going to be a phenomenal panel in the meantime. Judges, please meet me in the judging room. And we will convene in about 45 minutes for the results. Something else I failed to mention is all of these projects were made in 3 hours. So yeah, this was a 3-hour hackathon, which makes it infinitely more impressive. All right, see you in 45 minutes.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Thanks.
Everybody, there's a switch on your mic. There is no too close. Eat the mic, please.
All right, guys. Hi, I'm Isabel. Thank you for that lovely introduction, Walton. I'm actually going to let my guests introduce themselves. I would say, well, I guess I'll do a quick introduction. We have Orcun, who's the CEO of Citrea, Robin, the creator of BitVM, Sims, the CEO of Alpen Labs, and Ariel, who is CSO of Fairgate. So thank you so much. Yeah, we're going to start with a little bit of sort of kind of positioning the four of you in the space and just kind of grounding into like who you are and what your companies are doing before kind of getting into the more detailed questions. I also promised to leave some time for Q&A. Is there a clock, by the way? Okay, awesome. Thank you. But yeah, I'd love to start by just asking the CEOs plus Ariel to just sort of chat a little bit about their particular brand of a BitVM implementation and sort of what makes you unique. I think that might be like a good place to start, is to kind of introduce your company and sort of what you think you're doing that's different in this sort of broader BitVM conversation.
Yep, this is open now. Orcun here, founder and CEO of Citrea. Citrea is the Bitcoin application layer that's actually powered by the first kernel upon Bitcoin. So the relation with BitVM is BitVM powers our bridge between Bitcoin and the Citrea as basically a layer 2 on top of Bitcoin. And with BitVM, probably Robin can explain better, but there are a couple more components, such as like the first component is the script that verifies the ZK proof, and the other component is the bridge, who coordinates all the signatures around this script and actually lets you construct different kind of light clients to move Bitcoin in and out to some layer. So for Citrea specific, we call our bridge Clementine. It uses BitVM in this core, but it's actually on the bridge side, it has some modifications from the actual code base and compared to the other code bases, which we believe makes it right trade-offs. There's always like, there's no best construction, I will say, but there's different trade-offs that a bridge can make. And for us, we believe we made the best trade-offs there to make it work well with Citrea.
Awesome. Sims, go ahead.
Hi, everyone. I'm Sims from Alpen Labs. So kind of a interesting, maybe fun fact, unknown. We started Alpen Labs even before BitVM. Obviously, BitVM was a fantastic breakthrough, and we engage and work on BitVM, BitVM 2 quite a lot. And I think in terms of, your question was like the particular way we're using this, right? So we were quite involved within the BitVM Alliance, contributing to the BitVM 2 implementation, whether through some papers that some of my colleagues you've seen, like Liam and others, worked on proving pairings to the implementation, and working out the bridging protocol as well. These are kind of two different things that we see it as, and often gets talked about in the same way. There's like, how do you resolve challenges, as Orcun was talking about, of arbitrary compute, and how do you build then a two-way peg using that core primitive. Where we are today is a lot of our focus is going to a garbled circuit-based design, which we call Glock. And the reason for moving towards that is really around, at the end of the day, we want to build the simplest kind of two-way peg and the most auditable and the most secure and transparent peg that we can make. And there's this is more recent work around garbled circuits, but there's this evolution of, I think folks call it BitVM 3 as well. We call it Glock, in very similar types of garbled circuit-based technologies. Really allows for that. I think not just the efficiency, but the security and auditability. So
thanks. Yeah, go ahead.
Hey, I'm Futo, and we were just talking about the origin stories. We were really focused on MPC. When we learned about the BitVM paper from Robin, we got really excited about that. We were also working on RISC-V technology and MPC at that time, and we kind of found a lot of interesting synergies between what we were doing and we have learned and the BitVM proposal. So we started working around the ideas of constructing complex programs that can be verified, and started dreaming about building a variant of a BitVM that we ended up calling BitVMX because we started choosing other trade-offs. And our positioning, if I have to define it shortly, is about trying to create a platform that would enable lots of possible applications that could be built by people that has some technical level that can benefit from having a proven, robust software platform to write these kind of applications. We are using bridges because it's what's more exciting. We have built a couple of bridges to guide how our platform should be, but we are dreaming of a more broad space of applications, and we are constantly thinking. Yeah, we're thinking about the differences. We ask about what are the differences. But I think there are a lot of similarities and common goals also in this room. Mm-hmm.
Yeah, absolutely. I was going to just ask you a more specific question, but you're welcome to dive in.
Yeah, I'm in it for the money.
It's my favorite Robin line, by the way.
What I mean by that is I believe in here what people have on their t-shirts, fix the money, fix the world. I know it's a bit of a naive dream, but I think life is better living it with such a nice dream in your heart. And I really think fixing money is that would be a great thing. And to fix money, we have to scale Bitcoin and also make it private. And that's why I was working on stuff like ZK coins, which is essentially a protocol to have private payments and scalable private payments, which eventually also was the inspiration for shielded CSV, which is kind of like the fleshed out version of the original ideas of ZK coins. And that requires some kind of bridge. It's essentially also a layer 2. And that's why I was interested in working on bridges and eventually came up with BitVM.
Thanks. I'm curious, Robin. My first question for you is going to be, as the creator of BitVM, but not necessarily affiliated with any company that's actually building a bridge on the commercial level, how do you see your role in this, in sort of shepherding this technology? Like, how do you view your own personal role and responsibilities in this broader ecosystem, given your sort of lack of formal connection with any of the commercial implementations?
I'm exploiting all these companies. Like, I'm working with their researchers and their developers, and I'm nerd sniping them into like helping me build these bridges that I need for ZK coins. And
do you feel any responsibility to this technology? Do you feel that you have like a pivotal, like, kind of like vertical to play in this, or are you just nerd sniping and
I'm engaging in the politics to some degree. For example, founding that BitVM alliance, I think that was a very important step because the ecosystem kind of like tended to fragment and like everybody built their own version of it, and I think that's like a losing game for everyone. So I tried to align the incentives of everyone and like make them contribute to one common implementation that everybody contributes to, and then they build their L2 on top of it, which makes everyone like win because a common implementation of essentially the core helps everyone to harden it and make it as secure as possible.
And the original implementation that you were sort of collecting around was this BitVM 2 snark verification implementation. Is that right?
It's in the beginning we also built a bridge, but it became very clear very quickly. It became clear that all of the L2s, they kind of like need their own version of bridge because it depends on which kind of side system you have. Some people want to build side chains, others want to build rollups, and next ones they want to bridge to Ethereum or whatever. And whatever use case you have, you need like slightly different bridges, and that's why we couldn't agree on a particular bridge implementation, but on the snark verifier in particular, that is common to all the bridges, and it was quite simple in the end to align everyone to contribute to that snark verifier.
Something that's been, I think, a very hot topic of this conference in particular has been this garbled circuits conversation, the sort of move that most of the implementations are making from using BitVM 2 architecture into some sort of garbled circuits implementation. Those seem to be less universal, right? So there's going to be multiple implementations, is sort of my understanding, by these different companies, or maybe I'm wrong, maybe the BitVM Alliance will continue with the sort of more universal garbled circuits implementation. I'm not sure. I'm curious like how you see the BitVM Alliance basically continuing its mission in a post-garbled circuits world.
It changed the game a lot because with garbled circuits, it's not as clear what the best solution is. In BitVM 2, it was clear this is the thing that we want to build, and everyone agreed that we want to contribute to that. With the garbled circuits approach, it was way different because it's not very clear. There are a lot of unsolved challenges, and that's why people started exploring all kinds of different directions. Also, there is a huge body of research on that topic, and exploring that body of research was also part of exploring what is the right solution for Bitcoin. But we are doing that in the BitVM Alliance. Essentially, everyone, like, all the researchers of all the companies of the BitVM Alliance, they pivoted to researching garbled circuits, but we are having these weekly meetings, we are having meetings at conferences, and we are sharing our research, and it's really a collaborative effort, I would say. People are contributing to a common knowledge base and exploring together the search space.
Do you see garbled circuits as an extension of BitVM, or do you see it as something different that's...
Yeah, BitVM is kind of like an ambiguous term. I would say, in that sense, BitVM is like a umbrella term for a set of tricks that together in combination enable bridges. And that's a lot of different tricks. For example, you have these Lamport signatures to introduce state. You have connector outputs to introduce state. You have this idea of using optimistic verification and challengers and operators and challengers. And you have like this how to build a light client and all these different components. And of course, you have that component of a snark verifier. And that snark verifier is, of course, the heart of it all. And that's essentially the toughest part. And like BitVM 2 was one way to build a snark verifier, and garbled circuits is another way to build a snark verifier. But all the other things, like all the bridge contract around that, is essentially the same thing. It's more or less the same kind of tricks that you need to build. And that's why BitVM 3 is kind of like the umbrella term of like using these kind of tricks, but with garbled circuits now. Of course, there are all kinds of different brands, and people want to position themselves and distinguish themselves, so it makes a lot of sense to also have different names for specific things. But I guess like on a high level, it's a advancement of the previous research and the research around bridges and the research about like how to have the most efficient snark verifier in Bitcoin.
Yeah, I'm curious, Sims. Obviously, I think Alpen Labs has sort of really made pretty like publicly clear that they are moving in this direction of developing this technology under the brand name Glocks, and perhaps there are technical and/or commercial reasons for that. I'm wondering if you could share a little bit about the decision to kind of maybe retract a little bit from the BitVM brand and this new architecture and sort of adopt this new sort of Alpen branded distinguished term that is Glocks that kind of Alpen can own.
Well, I think we thought Glock was pretty funny. Like it's like a it's a Glock. It's a garbled lock is what it stands for, and this also made intuitive sense for us as we thought about like we talked about this a little bit here. Of there's really like two kinds of things going on here. There's this kind of like primitive for verifying arbitrary computation via a snark. And doing that optimistically. And so there's a whole class of different solutions around it. At least this is how I see it. BitVM was a class of solution around it. The challenge resolution was, many, many rounds, but low on-chain costs. BitVM 2 was an incredible idea that brought this down to like much, much smaller, very tractable rounds, but more on-chain cost as to resolve claims about arbitrary computation. Then we just see Glock and these garbled circuit-based approaches as a natural extension of how do you, this class of optimistically verifying arbitrary computation on Bitcoin. Now, ultimately, even with BitVM 2, like we also call it, I'm not going to argue with Robin, the creator of BitVM's definition here of a set of tricks that enable these kinds of two-way pegs or bridges. But I find that definition difficult for myself only because pretty much every team has a different BitVM2. And so there's this. I think, as most people would understand it, maybe outside of the technical work, they would think, okay, it's the same kind of thing, but really, it's the same kind of primitive. But really with different bridge instantiations and even different sets of tricks. So like I know Fairgate has some incredible papers out around flex and around TOOP, which is solving some really important problems with the bridge constructions. Not everyone is adopting that. So yeah, I mean the reason for Glock was we thought it was funny and we thought it made sense in the context of hash locks. Are these kind of more simple kind of constructions. Garbled locks are the smart locks, so to speak. You can kind of unlock based on the validity of arbitrary compute.
Something that there seems to be some agreement around or consensus around is this idea that garbled circuits has essentially made obsolete BitVM2. Which I think leaves many of the commercial implementations with sort of the sunk cost problem. What do you do about BitVM2? We've already paid all this money for this audit. We've built all this stuff. Are you basically, I'll start with Sims, just sort of, we're kind of on you already. Are you guys planning to kind of abandon your BitVM2 and just like go head first into BitVM3, just drop everything and go forward with with Glocks? Or, are you taking a different approach?
We like BitVM2. We think it makes sense. There's just a lot of complexity relative to Glock around, we had to take a Groth16 verifier, implement it in Bitcoin script. That's already quite complex. So we're contributing to the audits, and it's certainly something that we're still keen on and interested in. But the direction that we're invested in much more, as we even get to mainnet, is around Glock. It's just, we want the simplest, most auditable, most secure option when we go into mainnet, and so that's the reason.
Would you say that it's fair to say that you intend to go to mainnet with Glocks and not with BitVM2?
That's the current, that is the current plan.
The plan. I'm curious to hear from you two as well on that. What are you doing there?
Yeah, I think there are like two different interests in a company that can arise in here, especially in our case. One is like the intellectual interest, and the other is the more business interest, I will say. So we have invested almost, I think, 2 years, or definitely more than a year, to BitVM2 implementation and a bunch of audits. And we already have basically the signers, or you can call it covenant committee, ready to launch the mainnet. So for us, there wasn't a reason to just like wait until the Garbled circuit research are mature enough and the implementation is there and everything got audited. So we simply wanted to just like go with BitVM2, which we already know the code base very well, and we have the integration with Clementine, and we have all the infrastructure partners ready for the deployments. So that's the direction we choose. But at the same time, we are basically still contributing a lot to the Garbled snark repo in the BitVM organization, which is the base of what we will use in the future for the bridging. So personally, I believe more on an iteration level where we ship something to the products people and get feedback on it and then improve. Even before getting feedback, we can understand Garbled circuits makes everything much more efficient and better. But just like going out, because the system doesn't only consist of just the bridge part or the verifier part, but it's the whole system that has applications on it. And we don't want to just like keep it wait until this research matures enough. So we can just ship the product, get feedback on the other parts while improving this part, so that everyone can win, including the users, testers, ecosystem players, and us as a company.
I think given where Garbled Circuits is right now on the research front, it's clear that that will probably help get you to mainnet faster in the short term. I'm curious, though, if you have any concerns about that maybe slowing you down in the long run, or, you know.
We were expecting to, I think, finish BitVM implementation beginning of this year, and it, like the audits, I think, just finished, right, a couple months ago. So there's a very high error rate, and like when you estimate some complex things like BitVM2 or Garbled circuits will be ready to use in production. So I think there's too much risk for a product company to take. So we definitely believe in that future and also put a lot of efforts into it. But it's just like a trade-off between you want to ship now and iterate on it, or you want to just wait to see if it's, even we don't know if it actually will work with all the parameters we set in our mind.
Yeah, well, I would like to add a couple of comments. I think that my perspective on this is that this is both an engineering problem and a research problem. And this space has a lot of innovation, so we can get, I don't want to say distracted, but we'll get really interested. And you said they're sniping. I think we really get very interested. These problems are really, really exciting. But if we want to construct a system that is going to be handling a huge amount of money, that is not a research terrain. That is engineering terrain, and engineering requires small incremental changes, but you need to do things in such a way that you are, of course, incorporating these innovations, but in such a way that you end up with a product that is robust enough to resist all of the adversaries that are going to be there because of the incentives managing this. So this is at the same time a complex problem because we need to balance these efforts of doing research and doing engineering at the same time, I think. And having something that is in a sense as backward compatible as possible, so that you can replace a modular replacement of different parts. I think that we're all thinking about maintaining part of the bridge design and changing like the dispute channel or the dispute mechanics, and we have been anticipating because we know we are seeing some of the drawbacks or the trade-offs with some of the solutions. So we're kind of anticipating. I don't know. Maybe Garbled circuit is like the final solution. How things are going, we might be discussing something completely different next year. That might be possible. I don't know. So, and I think that we are, in a sense, from the engineering point of view, we are kind of prepared for this. I mean, as researchers, we are really, really enjoying this. From the engineering part of our companies, they are saying, okay, calm down a little bit. Let us plan.
I'd like to add something on this. I think there's a nuance that's worth pointing out when we talk about garbled circuits. It's like an umbrella term, but really, it's I think when we came to this decision to put so much resource effort around Glock as it relates to the mainnet roadmap as well, the most important question we had asked was internally: are there any research problems open here? Any open research problems, or is this matter of engineering at this point? In our particular instantiation of this garbled circuit-based approach, we felt like the core research problems were already solved, which gave us kind of if we felt like that was not the case, it wouldn't have given us that kind of confidence to say, okay, this is a better kind of approach to take into mainnet, and it's also the path is there to be able to do it.
I think it's important to kind of think about okay, what are the real practical implications of this garbled circuits, tech jargon that we're jamming about? Obviously, that is the liquidity requirements needed by bridge operators. I'm curious how those conversations are going with folks on the bridge operation side for the commercial implementations. Are those conversations substantially changing? Are you getting new players who want to now participate in bridge operation because it's so much cheaper to play the game now? How have those conversations been going? On the commercial side, how is garbled circuits actually changing things for you?
Regarding garbled circuits?
Yeah.
Okay, yeah. One of the key benefits is the challenge resolution. The cost that it takes to disprove an operator in this scheme is dramatically lower. It is several hundred times lower than BitVM 2, and this has a direct kind of relation into how much bond is required as an operator to participate in this kind of bridge construction. So this is lowered by quite a bit. That's definitely opening up some conversations that were previously, we were looking at something like close to 5 Bitcoin bond that has to be locked up in the BitVM 2 construction. Here, there's significantly less. We are seeing at least 10 times less, and there are even new ideas that I heard just this week around even more dynamic ways to do this and not a static way. So using kind of a garbled circuit-based approach. And so I think that it's making, I mean, to conclude, it's opening up the type of operators that we have and the number of operators and the diversity of operators that we can have participate in this system. You know, of course, for some, like larger stake amount was no problem, and you know they were already in. But yeah.
Do you want to comment? Anyone else?
I would like to make just a small additional comment because of the slightly different trade-offs on BitVMX. We decided to go with when BitVM 2 appeared. We decided to go with longer challenge period, more rounds, but support smaller bonds and smaller costs at that point. And we decided, from at least from our perspective, it was worth to explore this possibility of having, a slightly less longer finality but lower costs. So from our point of view, Garbled circuit brings smaller costs, but the difference for us is really not that huge. For us now, the difference that we can do a single round challenge. So the perspective, I mean, the benefits are really interesting, but are different depending on the perspective. Yeah.
Yeah, no, that's a good point. I'm just curious.
Yeah, I was going to agree with Sims that it generally makes it easier from, especially not the signer perspective, but the operator perspective, because they are the ones who need to put the bonds. And also there is this now transfer of ownership protocol, which can also change the game of liquidity provisioning. So generally, when you combine this with Garbled circuits, yeah, you definitely get material benefits in terms of who do you onboard to your signer set or operator set.
Do you guys pick, like, are there specific criterion for how you pick bridge operators, or like, is that changing, like who you want to have be a bridge operator? I'm not entirely sure how it works, so I'm asking this on the fly.
I mean, generally with BitVM2, the bridge operator role is either like put a bond, basically a collateral, which is, in our case, I think it's 2.4 Bitcoin. And then they need to consistently add liquidity to the withdrawals unless we fail the optimistic payout role, which means if any of them, the signers are offline, then we need to fall back to that road. So it's a little bit liquidity heavy role that's not like a plain infrastructure company can do. It's more like a financial role. But with Garbled circuits, then it's still a financial role, but with less collateral.
How much? Like I know this might not be determined yet, but like what are we talking about in terms of like a requirement?
I mean, the bond is 2.4, I guess, in our case, like somewhere in that range.
Even with GCs, it would be the case.
No, with GCs
what would
lower.
it be?
Yeah, I'm not sure, maybe Sims has the updated numbers, but it should be less than definitely 1 Bitcoin. Yeah.
$100 should be fine.
$100 should be
fine.
fine.
Yeah.
Right, so it's just basically like at that point you're just picking operators based on like what?
Again, liquidity, because unless you implement something like transfer of ownership, there is still a liquidity requirement where they need to find Bitcoin to pay users and then wait for reimbursement.
I see, that makes sense.
And from our perspective, if this is required already with Garbled circuits, then putting 2 Bitcoin as a collateral is not an issue for such an institution who can always find 10 Bitcoin to pay withdrawals.
That makes sense.
To give you an understanding, like in these bridge contracts, there are 2 crucial transactions. There's the assert transaction, where the operator asserts to the proof, and then there's the disprove transaction, which allows challengers to disprove the operator if the assert transaction contains something faulty. And in BitVM 2, the disprove transaction was around 4 megabytes. And with Garbled circuits, you can reduce that down to 200 bytes.
Right, so the liquidity...
That's like more than 1,000x improvement, and the collateral was just for the disprove transaction, for the operator to put a collateral to get disproved if he's lying. So now the main part for which you needed the collateral is just...
Right, there's still collateral requirements, they're just not for that particular operation, essentially.
Yeah.
Okay.
It's just to keep them honest.
Sorry, there's still n-squared channels, right, between the operators and...
Well, channel's true, but you just need a single collateral.
As a challenger, you will need collateral and collateral for each channel, probably. As a watchtower, I mean, you're
but you don't need to lock that. Like the operator needs to lock during setup, but the challenger, they provide it in case they want to do a challenge.
Well, if you support conditional conditional inclusion of the circuit inputs at some point. You might need to be able to, for the challengers to put some stake at that point. And if you still, I mean, maybe I'm a little bit picky, right? But you need to support, you need to have capital to be able to challenge every operator. So.
But the difference is if you have to lock that capital for like the entire lifetime of the bridge, or just for one single challenge in case somebody is malicious.
But you need that availability if you assume 1 out of n. It's a small detail, but
you have to be able to pay that capital, but you don't have to lock it. Yeah.
I'm curious also, some of you are doing kind of like a more modular style implementation where you're like kind of plugging into other L2 environments, for lack of a better word. Some of you are like not doing that, you're just going full, we're a roll up, that's it. Do you want to share kind of what your strategy is and why you picked that kind of direction?
So the Clementine is built for Citrea, but obviously it's a technology that will probably be commercialized like in a year or two for across all the bridges that's built. For us, Citrea is the first and only priority, so we don't have plans to just like have other chains use the bridge. If they want to, they can, but this is not something that our company do.
We haven't shared much around this, but we're building the systems we're building today. It is being built like it's designed basically to be a shared bridge that multiple execution layers can access. And the way that we think about this BTC generally is we want it to be the open standard BTC in any kind of programmable context, any programmable chain, as opposed to, let's say, CBBTC, which is the closed standard BTC, or WBTC, which is the closed standard BTC. What I mean by that is, we look at the one of n assumption around this. There are a bunch of custodians, non-custodial wallets, exchanges, etc., that want to tap into various kinds of DeFi protocols that might be only available in more programmable chains, whether that's Bitcoin-backed loans or whether that's yield or some other kinds of things. Today, the way that they can do that is probably, if you're a custodian, you hand off your user's BTC to another custodian, maybe Coinbase, that's probably your competitor, and then get access to those protocols via Base. No one wants to do that. I think the industry adoption will happen with a one of n style protocol. Eventually, we need to make it trustless. This is the best that we can do under the current constraints of Bitcoin. But even the one of n allows for these different maybe call it distribution partners or different exchanges, custodians, etc., to be part of that signer set, the operator set. So they are one of the n, they don't take additional counterparty risks, and neither do users that might be already trusting them. And so in that vein, we also want, this bridge, like the positioning of this is, it is the open standard BTC. It is not the closed standard, and multiple ecosystems should be able to share this bridge and be interoperable with one another.
Great. Our approach is we are building BitVMX as a software platform. Let's say that we want to be able to enable developing different applications. The first two initial applications are two bridges. One we call Union between Bitcoin and Rootstock, and one we call Cardinal between Bitcoin and Cardano. Those are slightly different bridge designs. And we are kind of using these two projects as customers to the platform. This is kind of guiding the requirements for our development platform for BitVMX, and we are trying to make it flexible enough that will support additional projects in the future.
Awesome. I want to leave some room for questions, so I think this might be my last. But I guess sort of a big question that I have all the time, every time I'm thinking about this Bitcoin layer 2 movement moment that we're in, is that historically Bitcoin L2s, however you want to define that, have had some trouble getting adoption. And I'm wondering, do you think that that's only because of the lack of trustlessness or trust minimization? I mean, so much of the branding around BitVM revolves around trust minimized bridging. Is that enough to actually get users comfortable? Is there something else that needs to happen to actually generate demand for these technologies? Like, how are you thinking about adoption?
I think it's like a very small part of it, I will say. It is an important building block for developers to understand on the platform, but not necessarily the users. I think basically as a platform, we are hosting developers. And if they basically understand this platform and these trust assumptions, they will be more encouraged to build on this platform rather than building on Rep BTC on Ethereum. And if you can basically get those kind of developers who are smart enough and capable enough to understand the technology and build on it, then the bet is basically the products they will build will be accessed by millions of other users, maybe existing Bitcoin users, maybe existing Rep BTC users, or just brand new Bitcoin users that will buy their first Bitcoin on this platform, who is more close to the native Bitcoin but doesn't have all the hassles of L1 trying to buy a L1 Bitcoin. So it's, I will say, more towards developers and power users who understands the platform, but it's also like a very small, like if you just build this, okay, I built the best Bitcoin out there, come build on it, then it becomes very hard to actually sell this piece of infrastructure because it's not necessarily the end user product. The end user product is the applications which is built on top of this Bitcoin and platform.
I'm kind of happy that I don't have to do that marketing. But on a high level, I can say I see that, like, in general, that crypto industry market is kind of like tilting towards Bitcoin because it's the superior asset, and ideally everyone would want to use that asset and not the other assets that converge against zero in comparison to Bitcoin. But I think like the first mover advantage of Ethereum is quite big. Like there is already a lot of established community and stuff going on there, and to move everyone to Bitcoin is a lot of effort.
Do you think that people are using, I mean, do you think that like the trustlessness specifically is something that people substantively care about, like the general user base? Like, do you feel confident that people will like make the leap just for trustlessness?
It's hard to say because I think we haven't seen a trusted Bitcoin L2 that does marketing really, really well. Yeah. And if we had seen that and had seen them fail, then it would be easier to answer that question. But we haven't seen that so far, so it's hard to make the comparison.
Too many variables, yeah.
Our initial strategy is really to kind of meet Bitcoiners where they are. And what I mean by that is partner with a lot of distribution, you know, like distribution partners, whether that's wallets, exchanges, custodians, et cetera, and offer things that they can't get otherwise, you know, through the applications that are deployed on Alpen. You look at like where BTC, you know, wrapped BTC is growing the fastest today. It's on Base, it's CBBTC, it's, you know, primarily through Morpho product for Bitcoin-backed loans. Why is that growing so much? It's because Coinbase has amazing distribution, has a lot of users, and directly on their platform, they have a ability to go and borrow against Bitcoin that is powered through these lending vaults on Base. Distribution is so important, like to be able to create those kinds of experiences, you know, in different platforms where people already might have their Bitcoin or might bring their Bitcoin to access these kinds of things. And of course, UX is part of that as well. You know, the alternative is like I would go get a MetaMask and try to, you know, use Aave or some other, you know, Compound or Morpho on their web app, and like this is just not something Bitcoiners are as familiar with, or even if they are, there's a hesitation there, and so you know our answer to that would be focusing on the UX and partnering with, like people that have distribution. And that's also like a place where they want the open standard BTC in this programmable chain. They don't want, you know, closed standard BTC.
I will give a little more dreamy answer. I think I like to think that Bitcoin users are really into
They're sophisticated people who care about trustlessness.
When the secure solutions are there, they will come. And I think that part of the excitement around BitVM that we are seeing since 2 years ago is because we think that this difference in security assumptions will matter in the end. I really hope, I'm invested that this is the world where we are. We still don't know because until things are really built and the UX is really resolved, we don't know how this will result. But I really like to think that this is really the Bitcoin users are going to really value this. Yeah.
Thank you. I could keep going, but we only have 2 minutes. So I just want to see if there are any questions from the audience. If not, I will finish my questions that I have. Do you see anyone, Walton? Oh, super. Go ahead.
When BitVM 4?
That's a you question.
Well, I talked to Mika today. He's working on like
I was going to say right before the BitVM 3 audit
encryption,
finishes.
witness encryption kind of stuff, and I'm trying to establish the saying Bitcoin researchers will solve witness encryption instead of going to therapy. And for those who don't know, witness encryption is like the holy grail of cryptography, and like indistinguishability, obfuscation, and stuff like that. I guess that it might happen, yeah. Also, Liam, who actually understands what I'm talking about, I am not understanding what I'm talking about. He says it's not unlikely that this is actually true.
Can we set up a prediction market maybe for BitVM 4?
Yeah, let's do that. Can I ask a question? Yeah. I don't know. What is the VM in BitVM 2? I've always wondered about that.
It's like it makes no sense at all. Like the first version, yeah. Well, like the first version of BitVM was actually a virtual machine, and then like that brand kind of got established, and that was the name of the Telegram channel. So like,
it's a strong meme.
We just stick with that. But there is at least there's a VM in the proof system. So, and at the end we are verifying that. So it's kind of like a VM. And it enables universal computation, so I would argue it's kind of like the
VM
same
vibes.
Pretty much VM vibes, yeah.
Nobody's complained about GPT, so I don't think why we need to.
Is that it, Walton? Are we done? I think we're at time. Alrighty. All right, thanks guys, that was awesome.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Did you have a nice conference?
Do we scale Bitcoin? I think is the real question.
I think we did it. I think we're done. I think
Does
Bitcoin.
it feel scaled? Or should we take a poll? Is that how consensus works?
Yeah. So raise your hand if you think Bitcoin is scalable.
All right, that's a lot of people. Cool. So we've got one quick thing to do. People are wandering in. Are we waiting for teams to still arrive? Okay, cool.
You know, this really was an incredible conference. How many countries do you think people came from?
At least 5.
5 countries. Incredible.
Maybe 21. I don't know. Are we
Yeah, who
betting?
here came the furthest? Who here thinks they had the longest plane ride? My flight was 11 hours.
Was that just sitting on the plane 11 hours? Or are we counting like time in transit or time on plane?
Let's do transit. So my
Time in
direct flight
transit.
was 11 hours.
11 hours. Can anyone beat 11 hours? I know at least one person. Okay, yeah. At least one person can beat.
That's 18 hours. 26 hours. Incredible.
All right, that might win. Yeah. Let's go here. Warsaw is halfway between here and Berlin or Germany somewhere. Yeah.
Cool. Want to start?
Are we ready to go? What are we doing here? Are we closing? We're closing. This is the end.
Yeah, this is the bookend to the conference. Let's end it well. All right. Well, before we officially end the conference, we have one last thing to do, which is announce the winners of the hackathon. So we had a 3-hour hackathon. It was incredible. We had a bunch of phenomenal teams and some incredibly impressive projects. Let's take a quick moment to recognize our star-studded panel of judges, some of the best and brightest. Yeah, thank you all. And it made a big impact on hackers to be judged by you. Nifty, how do we judge projects at B++ hackathons?
Yes, we use a modified women's gymnastics competition scale. We judge people on 3, I think, actes. The first is routine difficulties. So this is how difficult of a project or movement were you attempting to make in code for the hackathon. So is it an ambitious project that's going to change the world, or is it something that maybe someone else has thought up before? You would get less points. The next category is routine execution. So this is, okay, given what you've set out to do, how close were you to actually accomplishing it? Do you have a working prototype? Is it shipped, ready to use by users? Or is it a wireframe drawing or a sketch on a piece of paper? And then the last category is something that we added specifically for Bitcoin++ hackathons, which is something called general effect. This is swag factor. How applicable was the project to the conference theme? So that would be scaling in this case. And, you know, general, like how well put together was the presentation? Was it easy to follow along? Did they have a compelling, maybe user story?
Amazing. So, Moving on to the prizes and challenges. Let's first announce the best use of Stark. So quick shout out to Starkware. This is the coolest thing ever that Starkware threw in this challenge. We've been dreaming of having cool tech companies do cool challenges with their technology and being a part of the hackathon with us. So really this is a dream come true. Thank you Starkware for being a part of this hackathon. All right, and for the projects that best leverages Starks for Bitcoin or its ecosystem, Lightning, Nostr, Cashew, Arc, Liquid, etc., goes to Bridgester. Congratulations.
Do we have a? Oh. Congratulations. Yeah.
Congratulations. Yeah, thank you.
Do we have a? Okay, thanks. Yeah, we do have stats for you. Those are in the mail.
Cool. Moving on. Next up is Best Beginner Hack.
So this prize goes to the team with the people that are newest to making contributions or committing code or creating code projects. Maybe this was their first hackathon in some cases.
Or among the teams, this is the best of the beginners.
Best of the beginners.
Yeah.
So standout entry to the space. And this goes to
Vlog
Swap. Congratulations.
Congratulations.
Do we have a?
Vlog Swap, are you here?
Yeah, he's right here. Come on up, Rocco. This one. Oh yeah. Cool. Congratulations. Yeah. Thanks.
Congratulations, Vlog Swap.
Congrats, Rocco. Really well.
Next up is Best Privacy Hack for the project that best protects privacy, evades censorship, or empowers free expression in hostile environments. This prize goes to ZK Poor. Congratulations.
Congratulations, guys.
Moving on to the Reality Check Award, winning tickets to future Bitcoin Plus conferences. For the team whose project could realistically launch and attract your users on mainnet soon, TM, goes to MergeSync.
Good job. Ambitious is this one. Congratulations. Yeah, well done. MergeSync's pie. Is it key lime or, I don't know, pumpkin pie? No, sorry. Bad joke. Okay. Next up is Moon Math Award. So this goes to the team with the boldest or most novel exploration into cryptography.
Goes to Racky Wallet.
Good job, Racky. Is this quirkiest? There you go. Cool. Yeah, congratulations.
Moving on to Best Design, winning a Blockstream Jade. We're super happy to partner with the Bitcoin Design Foundation to promote good design in Bitcoin. So they've been helping us with picking design winners and promoting good Bitcoin design in our past few hackathons. So we're super thankful to have them involved. So for the project with the most intuitive, polished, and visually appealing user interface or user experience goes to ArtMock.
Thank you.
Nicely done. Very cool.
Cool. Moving on to our honorable mentions. These are some projects that were phenomenal and deserved appreciation on all of the overall categories. So these are non-denominational, unspecific, but generally amazing projects. And they all win Bitcoin Plus tickets. So the first honorable mention goes to CrediLink.
But we want to just get, we unfortunately don't have prizes. We just have tickets. Yeah, cool. Thanks.
The next honorable mention goes to Bridge Agent.
Good job.
That's our honorable mentions. Okay, moving on to the moment.
Should we get another round of applause for everyone? That was really cool.
Yeah. Amazing round. Okay, moving on to the best overall. This is the moment we've all been waiting for. So a recap. This is a massive prize pool of 5 million sats going to our top three. Third place wins a SICK trophy, 1 million sats, Bitcoin Plus tickets. Second place wins the trophy, 1.5 million sats, and Bitcoin Plus tickets. And for the overall top prize wins trophy, 2.5 million sats, Bitcoin Plus tickets, and a sponsored flight to the Berlin Lightning Plus conference. And also they walk away with the title of the winner of the official Bitcoin Plus Scaling Edition Hackathon. So, starting with third place goes to... Actually, let's have a few words before that.
So I want to take a moment to thank our sponsors. We couldn't make these conferences happen without them. So big thank you to NIDIG and the Human Rights Foundation who made not just this event, but all the events that we're doing this year possible. I'm very grateful for their support. We also had one last honorable mention that we forgot a little bit earlier. I want to give a big thank you to Isabel Foxenduke for her work in helping put this conference together. Isabel, are you here? I don't think Isabel's here. She must be taking a well-deserved nap because she put so much work into not only getting an amazing crew of speakers and sponsors here, but making sure that the event had, I think, a really great conversation at the end and moderators. So thank you, Isabel. What else have we got? Oh, a few small announcements. We're doing a kind of closing after party today. There's another event that's going from 10 o'clock. There's another event happening tonight that's like the BitVM Alliance. So I think that starts at 7. This will be like at 10 o'clock. We're going to hang out at Balkan Bar, which has a nice rooftop. So come get some drinks. Also, thank you to everyone that puts up some sats to help pay for drinks for people. So we hope to see you there for an after party around 10 p.m. What else have I got? Oh, right. So this was a really great event, but we have a couple more events happening this year. Really excited to have this one done. Thank you for making it a huge success, but I hope to see you all at our next events. The next up, most recent, will be a Lightning Edition, our first Lightning Plus happening October 2nd to 4th in Berlin, Germany, right next door. So hope to see some of your familiar faces there. All right, Alex. Without further ado.
Yeah, what were we doing? Lost my train of thought.
Oh, that's right. So coming in third, gets the drum roll,
winning 1 million sats and Bitcoin Plus tickets, and the title of third place at Bitcoin Plus Scaling Edition goes to ZK Poor. Congratulations, ZK Poor. And winning second place, 1.5 million Satoshis and Bitcoin Plus tickets goes to Core LLM.
Okay. Congratulations, y'all. It's a really great project. I'm going to learn so much about Bitcoin Core through this, I think. Very exciting. Cool. Thanks, guys. Yeah. We'll get your tickets.
And first place overall in the title of winner of Bitcoin Plus Scaling Edition goes to Artmark.
Congratulations. Very well done. Yeah. Okay, I see, yeah.
Vertical.
Very well done, yeah. Great.
Well, that was amazing.
That
Thanks,
was a great
everybody.
conference. Thank you, everyone. Hope to see you later tonight and in the future at another event.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025.